Am I audible?
Yes.
I think there's a technical glitch in between. It is just creating some issues. Uh, Sir, your doctoral research was focused on the design and modeling and characterization of electronic devices, optoelectronic devices, and electronic photonic ICs. Sir, you're also proficient in using various EDN CAD tools for nano device design, modeling, characterization, and analog mixed signal circuit design, simulation, and optimization. Your vast area of experience is truly amazing. Sir, now without delaying in my speech, I would like to hand over the session to you. Over to you, sir.
Thank you, Jari, for the nice welcome. Hi, everyone. Good evening. So today I'll start my topic that's integrated photonics for energy efficient computing. So let me get started. Can all of you see my screen okay?
Yes, sir, you are visible.
Okay. So what I'll do today is go through some of the integrated photonics, what it can do in the computing world, and I'll also give one example of one of the examples which I did during my PhD dissertation. That means we designed a fully novel hybrid 6 transistor electronic photonic SRAM. So I'll just give you an overview of what are the things, what are the prospects, how much advantage in computing we can get through the hybrid structure over the regular structure. So let me get started. So the outline of today's talk will be first introduction and background of why photonics, what is integrated photonics, why electronic photonic integrated circuits, and a slide about silicon photonics. Then will be our objective and understanding the LET. So that's the prime thing of today's talk, the light effect transistor. So we developed a fully novel structure called a light effect transistor, which is similar to the field effect transistor. We will discuss in detail about the light effect transistor. And we will also, give me one sec. Let me just do the pointer, laser pointer. Yeah. And we will also discuss this LET, light effect transistor, how we can use it to replace some of the field effect transistors in conventional electronic circuits. Now, then the LET design and modeling, followed by application of the LET in the 6 transistor SRAM. That's the primary the primary topic of today's discussion, application of LET in hybrid 6 to SRAM. All these, both of these two. Then proposal of a novel 3D electronic photonic integration scheme. So this is also a very novel work which we did. It's not been done before. Like, we will propose a novel integration scheme for our hybrid structure. Then show some design of optical waveguide using commercial optical CAD tools. Then I'll present the design of a fully functional 1-bit cell of a 6 transistor SRAM. Then a brief example of how we can use optical or optoelectronic logic gates for the next era of computing. Like, you have heard about AND gate, OR gate in digital circuits. I'll do the same thing, but using light. We will just get a small overview from there. Then conclusion followed by future prospects or future possibilities. So let's get started. So the big question that comes to everyone's mind: will electrons or photons rule tomorrow's application? As you can see from this, like these pictures, taken from this research paper that photonics has already like getting much popular in today's world, basically due to few reasons. Like it can lead to much energy efficient transmission as opposed to typical electronic circuits, where whatever we do, we have the RC delays, right, in the electronic wires. Because definitely any electronic wire will have a finite resistance and capacitance. So whatever we do, whatever techniques we adopt, we cannot zero out the RC delay. And the RC delay leads to the energy consumption. So those things will be inherent to a typical electronic circuit. Also, as we will come subsequently, the advantages of photonics and the structure which we propose, which we developed, we will come to there subsequently. And as you can see, as time passes, photonics is also getting very popular. So here you can see most of the photonics has been used only for optical communications, right? That means basically you can think it as a optical waveguide. That means we have a photonic signal and we transmit the photonic signal through the optical waveguide to another part and then convert it back to electrical signal and do our job. So it's mainly about the transmission, right? Photonics, the optical waveguide is mainly used for the transmission, uh, but not directly in the computing. That means you have a part, you generate the signal, you transmit it, then you get it in optical form, generate it, convert it back to electrical, then do the work, right? So here we will present something different. We will use photonics into the heart of electronics, not only for transmission. What is an EPIC? Now, EPIC stands for Electronic Photonic Integrated Circuits. This is a typical and an awesome example of an EPIC. What is an EPIC? Like, that means it has electronic components as well as photonic components on the single chip, or monolithic integration of electronics and photonics on the single substrate, and such that both the electronics and the photonics, they perform in handshake, they perform together. So it's very much easy to understand. So this is a typical CMOS inverter. You all of you know it. It's a PMOS, NMOS, and a CMOS inverter. So it generates a signal. Then we will have or let's start from here. This is better actually. This is a laser diode. So this is a laser diode. You know, a diode or laser diode or
Sir,
Excuse me, sir.
I'll take you interrupt you, sir.
yes.
Your
Your
screen is not visible, sir. You are
Sorry.
visible, but your screen is not. I think there is some problem regarding the screen sharing, sir.
Oh,
You are
okay.
visible, but your screen is not visible.
I'm sorry. I'm sorry. Let me look at it. Can you see my screen now?
Not
Sir,
yet,
your
sir.
share screen is not showing.
Okay, okay. I got it, man.
So
Uh,
what?
so give me a sec. It's telling me some error has occurred while trying to share the screen. Let me do one thing. Let me just get out of the Google Meet and reconnect. Okay.
Okay,
I
sir.
think probably that will help. Probably.
Okay,
Okay,
okay.
Sorry for the trouble. I'll be back.
okay. Thank you.
Totally fine.
Hello, everyone.
Welcome back, sir.
Yes. Can you see my screen now?
Now it is in, sir.
Okay, sounds good. Let's get started. So this is a cartoon. Let me turn on my laser pointer. Yeah, this is a cartoon showing it's a great example of an epic. So you have a laser, like semiconductor laser or whatever laser, that generates an optical signal that passes through the waveguide. Then there's some optical modulator that modulates the signal, like we have for typical electrical signals. We have the frequency division, multiplexing, analog modulation, digital modulation, those type of things for the optical, like photonic signal or optical signal light is done here, followed by it passes through this waveguide. Then we have a coupler, it couples it to this waveguide. Then we have a photodetector detector. Now what's a photodetector detector? So most of the computations are done via electronics, right? You directly cannot use light for computing. So till now, so what is done in photodetector detector is it converts an optical signal into an electrical signal, and this is the electrical signal that again it's the input of the CMOS circuit, and that's how an epic works. So these are the areas, something which is called more than Moore. So all of you know Moore's law, right? Every 18 months, the number of transistors in a chip doubles. All of you know this, right? So we are at almost at the verge of, how will I say, like Moore's law not being applicable, because there are many issues which is not the topic of today's discussion, but some of the areas where we can use photonics instead of typical electronics are these areas. These are all of them are very hot research topic. So our concern here today will be somewhere here, like memory, or let's say hybrid electronic photonic memories. Now again, electronic photonic integration, what are some of the major challenges we face? Like photonics has been started since probably early 2010, till it's not as popular as electronics. There are some reasons, right? First is the size mismatch, then high energy data rate, then cascadability. Now size mismatch means all of you know electronic circuits can be miniaturized, right? So you hear about TSMC's latest 2 nanometer chip, which will be probably used by Apple in their upcoming iPhones. So even the Apple 16, the iPhone 16 uses probably the TSMC 3 nanometer process. So that means electronics components can be really miniaturized. Okay, now there is a misconception. Many people, 3 nanometer never means the gate length is 3 nanometer. It's kind of impossible to bring down the gate length to 3 nanometer. So I'm talking about 3 nanometer process. Now, Samsung claims 5 nanometer process. So in those processes, what's the actual gate length? You never know. You never know. No one knows, actually. That's industry secret. Now, if you ask me, then what is 3 nanometer? What is 5 nanometer? I don't know. Because now the problem is what TSMC claims to be 3 nanometer, a certain dimension. What dimension? It can be metal 1 pitch, it can be the gate pitch, whatever, but never the gate length. So TSMC claims, say, suppose 3 nanometer to be a certain dimension. It's never true that Samsung will claim the same dimension to be 5 nanometer or 3 nanometer. They use some different like measuring strategies. So these 3 nanometer, 5 nanometer, 7 nanometer nodes, whatever they use for marketing, they are basically meaningless, to be very honest. So below 22 nanometer, gate length are not scaled proportionally according to the node name. Okay, so that's where again deviating from the topic. So size mismatch means, now the problem with photonics or optoelectronics, you cannot miniaturize them, because whatever optical signals we use in visible spectrum. So if you recall, oh, can you please mute? Someone has probably unmuted. We are having some background noise. Okay, let me continue. So size mismatch means since optical signals like visible spectrum starts from ultraviolet till red. So in this spectrum, the wavelength, the minimum wavelength is around say 300-ish. There are some background noise. Can you please mute yourself if you are not speaking? Thank you. So that means the spectrum of light, with which we can do the photonics or optoelectronics, ranges from around, say, I don't have the number at the back of my mind, around 300 nanometers to something like some micrometers. So you can see that means the minimum wavelength of light, if it's not extreme ultraviolet, that's different. That's around 200 to 300 nanometers. That means we cannot scale down the device dimension below that, else it will have some coupling efficiency issues. So that means the size mismatch. That means we cannot miniaturize photonics down to the level we miniaturize electronics, because the wavelength of light is kind of higher than that. Then high energy data rate means high energy per bit rate. That's an issue. And the cascadability, that's also a huge issue. Like, how will I explain this? Like, you cannot cascade two optical components like we do two electronic components. Let's say we have a device. The output of the device is light, or yeah, it's optical signal, and we need to use that device to drive another device, right? Now, unfortunately, the input of the other device is electrical. That means we cannot use the output, which is optical, to drive the input, which is electrical. We have to go through a conversion. That means we cannot cascade two electronic two optical components together. So that's also an issue. Now, silicon photonics, it's basically using silicon and silicon like products or silicon compounds in photonics or optoelectronics. Now, why do we use silicon photonics? First reason, it's cheap. Silicon is very cheap. That's why it got popular. That's also one of the main reasons. And it's integrable. Like we have the CMOS, silicon CMOS, right? All the electronics, majority, I know, won't say all, say around 90% of electronics are made from silicon till now. So also, if you could do some optical devices using the same material which is used in electronics, so we can integrate it together without having problems. Now there are much more efficient materials for photonics, like gallium arsenide, indium arsenide. I have a quick question for you. Can anyone say why these 3,5 materials and 2,6 materials are better for photonics than silicon? Any idea? Anyone? Any idea? It's a very fundamental question. Okay, let me answer. This is because silicon is indirect bandgap semiconductor, right? While that means there is the maxima and minima of the EK diagram, the valleys, the conduction band valley and the valence band valley, they have difference of K, the optical, the phonon coupling thing, the momentum difference. That means silicon is not a great absorber or emitter of light, while direct bandgap semiconductors like indium arsenide, that's a 3,5 material, gallium arsenide, again 3,5, cadmium selenide, it's a 2,6 material. They are all direct band gaps and they are excellent absorbers and emitters of light. However, the problem is, since they are a different material than silicon, they are not group 4. Silicon is group 4, right? So they have some issues with directly integrating with silicon, cost issues, mainly cost issues. So industry is very, it always moves towards whichever is cheapest and gives decent performance. So people are rushing towards silicon electronics. That's one of the main reasons. Now, silicon electronics also allows everything on a single chip, because the electronic, like if you think of a photoelectronic or optoelectronic device, like it has the optics part, it has the electronics part, and everything is integrable on the same chip because everything is made from silicon. You don't have to do something fancy to integrate it on silicon like you need to do if it's some other material like say indium arsenide, gallium nitride, cadmium selenide, whatever. So everything can be integrated on a same chip, and this is a wafer. It's a like say let's say 300 millimeter wafer. So what are the things we have for integrated photonics? We have a light source, that's a laser. We have a light transport medium, that's an optical waveguide. Then some filtering, these are generally passive filters, okay? Generally passive filters. Unlike, the RF or the RC filters, the op-amp filter, those things are a bit different from that. Then again, a signal modulation and detection. This is a photon detector. Now, aims and objectives. Now, the objective of today's talk will be mainly, so there are vast, it's a vast topic, and there is no time. Like I only have, let's say, 1 more hour. So the main objectives will be here to discuss a novel photon detector structure, which we have developed, me along with my supervisor and the group members during my PhD. It's called a light effect transistor. So what's an LET? We will directly go into it. So to understand the physics, structure, and working mechanism of a light effect transistor, to estimate the performance of LET using known and measured parameters, to study the characteristics of an LET. Now, this is the most important part, to use LET in a 6-transistor SRAM, and proposal of a novel 3D integration scheme. I discussed design of optical waveguide and design of a fully functional LET, 6-transistor, sorry, not LET, fully functional FET-LET hybrid SRAM. Now, this is an LET. Now, this is I'll say we did not invent the structure. That will be lying to say like invented the structure. We developed the structure keeping in mind some photon detector physics and the basics of some optical physics and optical absorption in semiconductors. So this is a light effect transistor. This is a field effect transistor. Now, you can see like it's very similar to a field effect transistor. The main difference comes in the word light, L. Now, field effect transistor is a voltage control device, right? Because we have a physical gate and we give electronic signal or a voltage to it, and we develop an electronic field. That's why we call field effect transistor. This is an electric field. Here, we don't have a physical gate, no gate. What do we have? We have a semiconductor nanowire with 2 contacts at the 2 ends. And what do we do? Now, this is an electronic device or electrical signal control device, right? This is an optical control device. That means here we have a electronic signal or electrical signal as a control terminal. Here we have a optical signal or light that is shined on the nanowire, and based on the very well-known photoconductive mechanism, we generate electron-hole pairs, right? And we have the source and drain contact. We apply voltage at the 2 ends, which creates a lateral electronic field, and which pulls the carriers. And the carriers are accelerated in this nanowire, and we get current. Pretty simple, right? And it's structurally different from the FET. You see, we don't have the gate here. So we have a semiconducting nanowire with 2 metal contacts, the drain source, sitting on a silicon dioxide and a substrate. That's it. And here, the control signal is light. Photonics or optics, light. Because here, you see, we have the inversion layer formed here due to application of the voltage. Here, we don't have this. Now, how is it advantageous? If you recall, in a FET, we have the gate, this drain, this source, this drain contact, source contacts, everything. Here is the channel, here is the substrate or body, whatever you call it. I call it the body. Now, all the gate-related capacitance, right? So if you recall from your semiconductor device physics, like freshman course, not freshman, I'll say, junior or senior course, like third year, second year, third year course, semiconductor device physics, the gate controls the semiconductor FET, right? It's the control knob, right? However, there are problems. The gate, so there is a, now the whole thing in a FET depends on how much the electrical signal applied on the gate is coupled to this channel. And how is it coupled? There's a capacitive coupling, right? We have an oxide here, which has a capacitance Cox, right? Everyone knows that, epsilon ox over Tox. Now, that thing helps to couple the electronic signal from the gate to the channel. However, the problem is That capacitance also leads to, there are some unwanted capacitance, this gate drain overlap, gate source overlap. All these capacitance combines to increase the RC delay and energy consumption of the system, right? The R into C delay, the tau equals to RC delays, and the energy consumption E equals to CV square. That thing that as you increase the capacitance, the overall energy consumption increases, dynamic energy consumption. That thing does not happen here. How or why? Because we don't have a gate, right? We don't have a gate. We have a nanowire sitting on a very thick insulating substrate. So this silicon dioxide is pretty thick, like it's around 100-ish or 150 nanometers. So we don't have the gate. So we don't have any gate-related unwanted capacitances, right? Because there is no physical gate. So the question of the unwanted RC delay and energy consumption, which we have in fact, inevitable, it's gone. It's gone, totally gone. So this structure is much more energy efficient as compared to this guy that we know, the conventional FET. So we will use this first, we will design and model this structure, and we will use this structure in the very well-known 6-transistor SRAM. Okay, let's move ahead. Any questions so far? I'll take a break, like a pause for 30 seconds probably. Any questions? Or I can go ahead.
Okay, sir. Go ahead.
Okay,
Okay.
sure. Now, working mechanism of an LET. I'll just give a brief overview. I won't bore you with those things. It won't be boring. I promise you that. So, how does it work? The source and conductivity is modulated by electronic optical signal. So in a FET, it's modulated by electrical signal. Here is optical signal of suitable wavelength. Definitely depends on what material you are using for the silicon for the semiconductor nanowire. So if you use gallium arsenide, you have to use a different wavelength. If you use silicon, you have to use a different wavelength. If you use indium arsenide, kind of different wavelength, but that's fine. We use an optical signal to generate electron hole pairs, and then we apply the electric signal at the two ends to make the move. That's it. Has a much simpler structure and does not have a physical gate. We discussed. Device speed is only limited by carrier transit time or RC delay, whichever is smaller. Or lifetime. Oh, sorry, not RC delay. Carrier transit time or lifetime, whichever is smaller, rather than the RC delay as in FETs. Now, once the carriers are generated in the nanowire, so there are two things that happening. Generation recombination, right? So there is if the semiconductor material is not absolutely pure, there is a probability that the carriers that are generated may be trapped. There are trapped states around the Fermi level. So they get trapped and their lifetime changes. Lifetime means, so what's the lifetime? The time, like how will I explain? So these carriers that are generated, they don't last forever. So the time till which they are inside the semiconductor, that's called lifetime, before they actually recombine. And again, like they are emitted as non-radiative recombination, they are emitted as photons. That's different. So carrier transit time or lifetime, whichever is smaller. Now the electrical switching energy of LET is pretty simple. It's like current flowing through the nanowire, the voltage difference we applied at the two nodes, and the TLET is the carrier transit time. That means how much time it takes for the carrier to reach the two electrodes. That's the time it takes for the carrier to travel the length of the semiconductor. Now the optical gating energy. Now this is different. This thing we don't have in terms of in case of a field effect transistor, right? Because it's a voltage control device, right? We don't have any optical signal. So this is an optical gating switching energy, I call it. It depends on the photon energy, the current that's again between the two terminals that's flowing, electronic charge. This is the gain of the photon detector, and again the electric transit time. Now this photon energy again depends on the wavelength of light, right? You know that hc over lambda, that formula, hc over lambda. The lambda is the actual wavelength of light. So if you use green light, it will have a different energy. If you use blue light, different energy. Yellow light, different energy. Red light, different energy, right? So this can be scaled down to quantum regimes without short channel effects. Yeah, because mainly the few short channel effects are the gate is there to mitigate those short channel effects. But since this structure does not have a physical source and drain, right? The LET which we told, like, we don't have a semiconductor implant of N plus or P plus, those regions, the diffusion regions. So that means they don't have the drain source. So the short channel effect between the drain and source, there is no question of short channel effects. And also this is like multi-beam, multifunctional illumination, which we will discuss in one slide. Now, LET performance estimates, I won't go into the detail. These are some results to give you a overview of what we can achieve with the LET. So the carrier transit time through the nanowire channel can be around 4.3 to 7.1 picoseconds for a 300 and 500 nanometer long silicon nanowire, considering an electron saturation velocity of 7 into 10 raised to 6 centimeter per second. For ballistic device, which we won't discuss much, a ballistic device means, okay, the collision between two carriers won't be there, because that's the minimum time required for that's called the ballistic device. Means basically there will be no collision between two carriers. That means the carriers which are supposed to lose their mobility due to collision, that won't happen. The carriers will travel with almost zero loss of energy. That's fine. Then again, the electrical switching energy using that relation which I explained in the last slide could be as less as 1 attojoule per switch at 1 micron current and 1 volt. The optical gating switching energy, which we again discussed in last slide, it's extremely low, like 2.5 into 10 raised to 3 attojoules per switch. This is green light, by the way, green light illumination, like 532 nanometer and a gain of 1000. So the total switching energy, what's the total switching energy? Is the summation of these two guys, okay? Electrical and optical. The total switching energy is around of the order of 0.1 to 1 femtojoule per switch, which is again pretty less compared to typical, like 2 orders of magnitude better compared to typical FETs. Now, directly jumping into the LET design and modeling. So the LET design has been done in Synopsys Centaurus TCAD. Probably many of you know this tool, right? You have used it during your academia or even in industry, it's used. So we designed LET structure using these tools. Like Synopsys has many tools like the S process, SDE, S device. We use the SDE because S process is more accurate, I know, but it's very complex and it's very computation hungry. Like if you don't have a kind of something like a cluster computer or a kind of supercomputer, it takes around hours and hours, more than 48 hours to do a process simulation. If you don't have very high-end computing system, extremely high-end. So we use SDE. It also gives awesome results, but it's not that computation or power, like computing power hungry. So we designed the whole thing in the Synopsys TCAD, did a mixed mode simulation of the hybrid 6 transistor SRAM. We will come to that. So this is some structure showing the device meshing. So this is a FET, conventional FinFET, and this is our structure, the LET, the light effect transistor. Now, some of things I'd like to discuss. So we designed a FET, a FinFET, as well as a LET in Synopsys TCAD. So we found, so this is a FinFET structure. We found that, okay, so fundamentally the current should flow here, right? In a FinFET, we have the gate wrapped around. It's a three gate structure, right? It's a 3D structure. Fundamentally, it should flow from this fin. This is the fin. The fins are basically the source and drain. And this structure, whatever we have there, is the body of the FinFET. So we found from simulation that the body also has very high current density, right? Now, this is something which we don't want. We want in a FET the current to flow through this region only, not through in the vertical direction. While if you see in the LET, we don't have any current in the body, right? It's almost, what's the value? It's, I believe, it's around 10 raised to negative 30. 10 raised to negative 30. And it was 10 raised to positive 2. That means we have a huge, like, huge saving in the leakage path or leakage current. We don't have any current flowing into the body. Why is this so? Because here, if you see, you apply voltage here. So we have a vertical electric field. That means whatever you do, and you don't have any insulation here at this point, like the three edges are covered, but this point, this is the whole body, the same connection of the semiconductor. So whatever voltage you apply here, there is vertical electric field. So there is bound to be some carriers or electric current leaking into the body. Here, no question of any vertical electric field, right? We don't have any gate structure here applying a vertical electric field. We apply electric field only in the horizontal direction, and we have some optical signals here and a very thick silicon dioxide insulator. So there is no question of any current in this structure or moving vertically from this nanowire into the body, right? That means this guy can offer huge energy saving during switching. Now, of course, if you have a single of these guys, a single FET and a single LED, doesn't matter much. But if you think of a VLSI circuit, which has millions and billions of these devices, then it matters. Now, this is some, I am again having some background noises. Can you just mute yourself if you are not speaking? Thank you. So this is a transfer characteristics of a FinFET and a LET from simulation. So you see in your transfer characteristics, you know, right? It's the drain current over gate voltage, right? At different drain voltages. So this is for the FinFET, and this is exactly for our LET. Now, you can see they're very similar. The only difference is that this is a voltage control device, right? Therefore, we have a gate voltage here, drain current here. It's a light control device or optically controlled device. Therefore, the gate voltage, we don't have a gate voltage. We don't have a gate actually, right? What we have is the optical generation or optical power that acts as the gate knob, right? The optical gating thing. It's similar, equivalent, not similar, I'll say equivalent to what we have in case of a FinFET. So we have the drain current, we have the optical generation or the optical gating signal, which behaves as the gate, and we have various drain voltages. So here we have 2 drain voltages, and we have like I chose 1, 2, 3, 4, 5, 6 drain voltages. So they are operationally, they are very same because they have the similar transfer characteristics. Now this output characteristic. So what is an output characteristic? The drain current and the drain voltage in the x-axis, drain current in the y-axis for various gate biases, right? Like as we increase the gate voltage, the drain current increases because again, this is a voltage controlled or a gate control device. Similar thing happens there, equivalent thing. We have a drain current, drain source voltage because we have the drain and source. Remember, we have the source and drain metal contact. We have it. Not the physical drain and source in the semiconductor diffusion, not that thing, but 2 metal contacts. So we have a drain source voltage, current, and the gate voltage is not there. What we have optical generation, optical power. These are optical generation rates, and these are the equivalent optical powers. Now, this is like when VG is 0, as you know, this is the off state, right? Because it's a gate control device, off state. The transistor is off. Same thing happens here. G is 0. That means the optical generation current is 0. Optical signal is 0. I'm sorry, not current, optical signal. That means the light which we are not shining, any light on the nanowire. That means it's in dark condition. That means the device is off because we don't have any carriers that are generated. Now, okay, one thing which I forgot to mention, the nanowire which we use for simulation is undoped. Okay, if you dope it, there is a problem. If you dope it, the dark current will increase. Okay, so it's fundamentally undoped. Okay, it's a almost intrinsic semiconductor. It's not doped. Now here are some. So this is some simulated results. Here are some actual lab measured results for a prototype 2.6 semiconductor. So here during simulation and all our designs, we have used silicon, but in the lab, actually, we use some other material, 2.6 material, because we found silicon, yeah, it's not a great absorber of optical energy. So therefore, we used a direct band gap material. Like I remember it's basically, yeah, Yeah, it's cadmium selenide. It's a 2,6 material. It's a direct band gap material. And here, these are the dimensions we used in the lab. It's huge, I know. In simulation, we have used much smaller structure, but this is a actual, like, if you have like thoughts in the mind, is the structure like simulation, we can do things, right? But does it actually work? Does it actually emulate the transfer and output characteristics of a field effect transistor? Yes, it does. We have experimental results. Here is the output characteristic. Here is the transfer characteristic. Okay. Now applications in 60 SRAM. That's we will discuss. Now this is a very like basic 6 transistor SRAM. All of you know this structure, right? Okay, a quick thing. If you need a break for a couple of minutes, just let me know. Okay. If you need a break for a couple of minutes, because I know it's a pretty long thing. So if you need a break, just let me know. Okay. So it's a 6 transistor SRAM. So this is the core 4 transistors cross couple latch. It's a cross couple latch, and these are the access transistors. This is the bit lines, and this is the word line. Okay, it's a basic, very basic textbook 6 transistor SRAM. What we did, we replaced these two guys, M5 and M6, with the LET, the light effect transistor, and the electrical word line with an optical waveguide. I'll come to that. So this is the read and write operation. As you can see from these cartoons and these arrows, these access transistors, they play a huge role in the read and write operation. This is a 6 transistor SRAM array. Fundamentally, it's pretty simple. You have these columns and you have the rows. These are the word lines. These are the bit lines. This is a 6 transistor bit cell. It's like explained here. How does it actually look? And the main thing to note here is that these two capacitances. This is the word line capacitance. This is the bit line capacitance. Now, what's the word line capacitance? This is the word line, right? What's the total capacitance? Now, this is an array. So you will have, let's say, thousands and thousands of such cells in a row, and also thousands of cells in a column. So what's the total word line capacitance? So these are the 2 gates, right, for a field effect transistor. So here we will have the gate capacitance as well as the electrical wear capacitance, right? Because it's a metal wear after all. So why 2 gate capacitance? Because if you see, a single bit cell has 2 field effect transistor, 2 FETs. So they have 2 gates. So 2 gate capacitance plus wear capacitance into NC. What is NC? The number of columns. So 1, 2, 3, 4. If you have 1,000 columns, so it will be multiplied with 1,000, right? And this is the bit line capacitance. What is the bit line capacitance? Now, if you see, this is a bit line. What's the bit line capacitance? The drain capacitance of this guy. Drain capacitance plus the electrical wear capacitance, right? And NR, what is NR? The number of rows. Clear? 1, 2. If you have 50,000 rows, it will be multiplied with 50,000. Okay. Now, very fundamentally, reducing the capacitance minimizes delay and energy. Now, how can we do that? So first, let's model the total energy and delay of a 6 transistor SRAM. Now, these are not developed by me. I got this from a research paper, but we developed our own equations from these. This is the background equations, okay? Depicting the energy and delay, the read energy, write energy, read delay, write delay of a regular, nothing fancy, just a regular 6 transistor SRAM array. Array means there are like thousands and millions of such 6 transistor cells. These are one cell. There are millions of such cells in the whole structure. Now, what we will do is, now I'll come there. Now, first, let me discuss what are the conventional ways to reduce energy and delay consumption in SRAM. So these are some of the conventional ways. Now, we can use larger current in the SRAM cell to decrease the delay. That's obviously possible, right? But the problem is, if you use larger current, the overall dynamic power dissipation increases. Now, you may argue with me, it's a single cell, does not matter. If it's a single SRAM cell, does not matter. Even if the current increases by 50%, does not matter at all. Power increases by, let's say, 1.5 times, does not matter. However, in VLSI, very large scale integration, we don't have a single cell, right? In SRAM cell, we have, depending on the size, say 256 kilobyte, 512 kilobytes, 1 megabyte, depending on the size, we have, say, millions of those, 100,000, 500, half a million, 1 million of those cells. Now, increasing power of a single cell does not matter. But if you multiply that number with 1 million, or say 100,000, or say 500,000, half a million, that's a huge number. That's gonna make the chip crazy, crazy hot. It's gonna misfunction. So that's the problem. So increasing the current to reduce delay, not a solution. Decreasing voltage swing to reduce energy, not a solution. Why? If you decrease the voltage swing, okay, the overall dynamic power dissipation decreases. Perfect. What's the problem? The noise immunity of the device gets crazily bad, not a solution. Also, there are many other techniques that some of them are described here. I got from this nice, the DAC paper. This awesome DAC paper explains. Some of the techniques are like word line overdrive or like negative ground. Those things are there, which are used to, how will I say, reduce power, increase speed, not sacrificing other things, but they need extra circuits, extra complexity. Now, extra circuit means extra space, right? And do we want our mobile phones to be thick like this, thick like a brick? We never want them, right? We want them as slim as possible. That means you have a huge space constraint, right? So cannot use. And even with all these things, we only achieve 25 to 35%. So that's not a big deal. So something we have to do, which is very disruptive, that's totally out of the box, which can do something crazy. Let's see. Now, this is our proposal, the hybrid SRAM. Oh, sorry. What we did, we replaced the access devices by the LET, the light effect transistor. And since the LETs are not electrically controlled device, we need to shine light on them, right, to make them operate. What did we do? We placed an optical waveguide here. Forget about the electrical wire. Forget it. Trash it. We used an optical waveguide, right? How does it help? Now, we will come to there. I have some numbers for you. We won't go deep into those things because that's kind of boring. I have to explain a lot of things. You won't get the feel in like half an hour. But the thing is that the electrical word lines we have, it has the RC delays, right? The RC delays, and as the length of the wire increases, the RC delays got crazily high. And if we could replace the whole thing with an optical waveguide, where fundamentally light travels through total internal reflection, right? High school physics. You remember high school physics? Light travels through total internal reflection. So almost zero energy dissipation. And about the delay, okay, you know, light travels, what's the speed of light through an optical medium? It's 3 into 10 raised to 8 over the refractive index. So it's in the range of 3, almost 10 raised to 6, maybe 10 raised to 7, which is much faster compared to electronics like drift motion of carriers. So this is what we did. That means the word line capacitance calculation, which we did in a couple of slides ago, it's gone. We don't have the word line capacitance, right? Because we don't have an electrical word line. However, we have the bit line modified capacitance. Why modified? Because you remember, for the last case, it was the wire capacitance and the source drain gate, the drain source overlap capacitance for the FET. Now, if you recall from the LET structure, we don't have physical drain and source, right? Because in FET, we have these implants, right? The N plus drain implant, drain diffusion implant, source diffusion implant. We don't have those. So those capacitance are almost negligible. We only have the metal semiconductor capacitance, which is kind of negligible, so we can neglect it. So we only have the wire capacitance there because the wire is still there. In the horizontal direction, we don't have electrical wire, but in the vertical bit lines, we still have them, right? So we have this capacitance. Now we developed few equations. This is fully developed by us. It's in this research paper. If you want to get into the details, you are most welcome to go through this paper. There are all details of how we got this and all. So we developed few equations to model the delay and energy of a hybrid electronic photonic SRAM. We developed this equation. And we did some numerical simulation to plot the read-write delay and energy of a conventional array and a hybrid array, which we proposed. And these are the results which we get. Now, in read delay, we have an average reduction by a factor of 4. In read energy, average reduction by a factor of 18. Oh, all these are published results. If you want to get into the details, you can either read this paper or I have a link to my doctoral dissertation. You can just go through it. It has much more detail. Similarly, for the write delay and energy, we have a reduction by a factor of 2, write delay, and reduction by a factor of 3 for write energy. This is the FET, this is the LET. Okay, and all the delays are in picoseconds and energies in femtojoules. Now, we went beyond this. What else can we do? Now, remember the array structure? Let's come back to the array. Yes, remember this structure. What we did is, now, if we could, so now there are concepts of, say, memory banking, which we won't discuss, like conventional SRAM, if it's a large array, very large array, like, say, lots of cells in the horizontally as well as lots of cells vertically, large array, let's say 2 megabytes of SRAM. That's a huge number. Now, okay, don't confuse SRAM with RAM. Okay, in your iPhones, you are probably saying, okay, we have iPhone 16 gigs of RAM. We have a laptop, say 32 gigs of RAM, right? Those are DRAMs. Don't get confused. Those are DRAMs. We are not talking about DRAMs here. We're talking about SRAMs. So DRAMs have very high packing density. So even 32 gigs, 64 gigs of DRAMs are possible. SRAMs, they are directly interfaced with the CPU. They are extremely costly. So 2 megabytes of SRAM is a huge number. Believe me, 5 megabytes, it's crazy huge. 12 megabytes, it's huge, more than huge. So we are talking about megabytes range. Most computers have it in kilobytes, 512, 1 MB. So if you have a large SRAM array, say 2 megabytes, 5 megabytes, that means you have to have large number of 60 cells horizontally, vertically. Now, some techniques which are done in circuit industry is called memory banking, like wrapping one layer on the other to decrease the size of the whole thing. Now, if we have large arrays and if we clip the number of cells in a column to, let's say, 512. How did I get this number? From industry and from literature. 512 is a number. If we reduce for large arrays, if we increase the number of cells vertically, there are issues. So let's clip or clamp. Let's clamp the number of cells in the vertical direction to 512. That means to maintain a 2 megabyte size, we have to increase it in this direction, because here vertically we can only have 512. So horizontally we have to increase large number of SRAM cells in horizontally. Now what's the problem? In regular cell, that means the length of the electrical word line increases. It goes crazy high, which means the RC delay and energy is uncontrollable, unthinkable. Huge energy, because as the length increases, resistance capacitance increases. As resistance and capacitance increases, RC delay energy both goes crazy, right? Now, I'll show you. That's for the regular structure. For the same thing, if we come to our hybrid structure, electronic photonic structure, let's say we clip it again to 512 in the vertical direction, and we increase the number of cells horizontally to large numbers, huge numbers. It won't matter much. You know why? Because now we are increasing the length of an optical waveguide, and light travels by total internal reflection at a speed of 3 × 10⁸ over this refractive index of whatever material we have used. That means 3 × 10⁸ itself is a huge number. If we reduce it by 1%, 2% due to the increase of this length, even if the delay increases a bit, it won't be much, because it's light after all, right? It travels at a very high speed. So the overall delay will be increased by 1-2%, tops 5%. insignificant increase of delay, doesn't matter. Energy, same thing. Light travels, total internal reflection, no dissipation of energy. That's why we use optical fiber cable in communications, right? In our internet, that's the reason we use optical fiber cables. No energy, almost theoretically no energy. There are dissipations due to some non-idealities like surface roughness, surface scattering, um, non-ideal coupling, but those are very less compared to the actual RC dissipation. So almost no energy dissipation, almost no increase in delay, right? So that's the beauty. Now, if I come to the results, you see astonishing results. For a read delay and read energy, if we could clamp in the vertical direction to 512 and increase in the horizontal direction for both the hybrid and the regular array, almost average improvement of greater than 2 orders of magnitude in read delay. In read energy, again, greater than 2 orders of magnitude. Can you imagine? More than 100 times improvement from like numerical simulations and calculations. And write delay energy, again, approximately 2 orders of magnitude improvement and approximately 2 orders of magnitude for both delay and energy. So that's a huge number. That means there's a huge probability or scope to actually use this, nurture these things in production. Now, EDP analysis, that's energy delay product. So that's the metric for all, like say, for an SRAM, I'll say, how much energy and how much delay. If you do the product, if both of them are very low, the product will be very low. If any of them is high, the product will be high. If both of them are high, the product will be crazy high, right? So again, we did some using these relations and some other mathematical tweaks, which I won't discuss here. We found for a like normal structure, we have almost 2 orders of 1 order of magnitude lesser EDP. That's also a good number. On 1 order means around 10. And if we have again that concept, that clapping the number of cells in vertical direction to 512 and increasing in the horizontal, we have a huge gain of almost 4 orders of magnitude lesser. That's a huge number, again, a huge energy efficiency. Energy, not only energy and delay, because that here is a product, right? Energy delay product. Now we will discuss something about leakage. Now these are the leakage components. These are the leakage components in a regular, or not a regular, it's a standard fact. What are the leakage components? The drain source, this junction leakage, some gate tunneling leakage, then gate source overlap leakage, and these are the GIDL, gate induced drain leakage, gate induced source leakage. And that's a punch through leakage directly between the drain and source. Okay. I won't go into the physics of this. There are lots of physics. It will take almost a week to explain this physics. So I won't go into the physics. You definitely know this. So what I'll do is, these are the leakages in a transistor or a FET, right? All of you know this. Now, if you think about our structure, the LET, what are the components that will be present? Can anyone say? What are the components that will be present? What are the components that would not be present? Any idea? Anyone? In case of LET? So, if it's an LET, everything will be gone. Believe me, everything will be gone. Why? We don't have a gate. We don't have a gate. All these red things, these are the gate leakages. They are gone. We don't have a gate. They are gone. All these three components gone. We don't have any drain body junction. We don't have any drain body source body junction. So these two guys gone. This gate induced drain leakage, gate induced source leakage, gate induced drain leakage. We don't have gate. So we don't have any gate induced leakage. Gone. Punch through, no concept of punch through in the LET. Why? We don't have source, we don't have drain. So there is no question of source, drain, punch through. Which one we will only have? This guy, the sub-threshold leakage. This will be there, which is equivalent to the dark current. Remember in the transfer, not transfer, my bad. In the output characteristics, we had the dark current. What's the dark current? When the light is not shined on the nanowire, the light is not there. No carriers, external carriers are generated. But we have the drain source voltage. That's the dark current. That's equivalent to the sub-threshold current. So only the green, the one in green arrow, this leakage will be present. Other leakages, totally gone, no question. Because of the, why? Because of the structure of the device. It's a different structure. It's a different device physics. Now, these are the, again, the leakage components in the FETs in a 6-transistor SRAM. Okay. Again, these are the gate-related leakages, subthreshold leakage, these are the junction leakages. Now, if we replace these two guys, as we have been discussing, M5, M6 with our structure, what will be the case? Boom, this is the case. What's that? Now, okay, now, don't misunderstand me. These things will be there because we have not touched the core components. We have not touched the core FETs. They will be there. We cannot do anything about it. However, since we have replaced only these two guys, all the leakage components in the access parts only, in the access transistors only, will be gone. Only thing that will be there, only the subthreshold leakage. So rough estimates show us, I won't go into the details of this because we are still working on this. We'll publish the results in a paper, maybe research paper. So I cannot discuss in detail, but rough approximation tells that there's a 35% reduction in the total leakage components throughout the single cell. Now, this number may not be large, but if you think of an array, which has lots of such cells, like say 100,000 such cells, then the overall leakage component reduction will be much higher. That will give to some benefits. Now, this is again a bit boring, but I have to discuss scalability. Now, I have mentioned huge numbers. I have given to tell you it can do this, it can do that. How much is the structure scalable or feasible? So you see these numbers, like how much actual optical power is needed to illuminate this, like optical waveguides, right? So if we use a 405 nanometer wavelength, now I believe 405 is it's blue light. Okay, it's blue. So how we can generate blue light? It's again indium gallium nitride laser. Because blue light cannot be directly generated from silicon lasers. No, it cannot be, because the wavelength of light coming out from a semiconductor depends on the band gap. You know the band gap, right? The EG. So the lambda is E equals to hc over lambda. So lambda is hc over eg. That's the band gap. So you just do some band gap engineering to generate blue light. Then that the most suitable is indium gallium nitride. Okay, it's a hybrid laser, like it's a ternary semiconductor. Indium is there. This is group. This is a give me a sec. Nitrogen. This is group 5. Again, these are like hybrid lasers. So if you use a 405 nanometer laser and this optical waveguide system, the silicon nitride, silicon dioxide optical system, it requires a gating power of approximately 35 nanowatts per LET to illuminate the whole optical waveguide, one single waveguide. And even if we consider loss of say 2.8 dB per centimeter loss, we still needs like only 76.5 microwatt of power to illuminate the whole optical waveguide. Now it's a very long. We have overestimated the length to be 1 millimeter. It's a huge length. Believe me, inside a chip, 1 millimeter, it's like 100,000 kilometers in reality. It's because the chip itself is in the nanometer range. It's in nanometer range. So compared to nanometer, a millimeter is huge, right? So it's 10 raised to 3, -3, and nanometer is 10 raised to -9. So almost 1 million, a difference of 1 million. So we only need 76.5 microwatts, and this power is much lesser than that can be generated by an optical laser, on-chip optical laser, indium gallium arsenide. So we are good. Now, this is a very interesting part, one of the best parts of our research. We proposed a novel 3D integration scheme. Like I discussed so many things, but how do we put them together? Now, this is a proposal, and we have a US patent. It's still pending. We have filed a US patent. It's still pending. For this structure, for this novel concept, we proposed, we filed a US patent. Now, this is a proposal. It's not yet productized, but this is a proposal. What did we do? You see how we can integrate the whole thing in a single IC, I'll say, integrated circuit. So here we have, this yellow thing, the lemon yellow. That's the, to me, I'll consider it as the optoelectronic part or optoelectronic layer. What are these? Now these blue boxes, these are the four transistor cross couple latch. These are field effect transistors. Remember, these are the field effect because we did not touch the field effect transistor cross couple latch, right? So they are there. Fine. These red guys, they are the LETs, right? These are the things which we incorporated inside the 6 transistor SRAM by replacing the conventional access transistors. And what we have these optical waveguides in a different layer, what we call the photonic layer. So this is just a cartoon, okay? This is a cartoon. This is the photonic layer, and we will have some openings. So you understand the vias, right? In electronic circuits, in CMOS integration, similar thing. Openings from the photonic layer into the electronic layer to illuminate these LETs, right? So this is the proposal or the conceptualization of the hybrid 6 transistor hybrid array in a nutshell. Now, what else could we have done? Again, this is a published results. Now, the problem is, if you come back to the previous slide, you see there are so many openings, right? So if we have 1,000 number of such of these guys in the row in the horizontal direction, and each guy has 2 openings. So 1,000 into 2, 2,000 openings. So from each waveguide, we require 2,000 openings, right? Now that's a problem. You know why that's a problem? At each opening, this is a waveguide, we have the openings. Waveguide, opening, waveguide, or waveguide moving in the horizontal direction, opening in the vertical direction. As the number of openings increases, there will be some loss at each opening. Coupling loss, or not coupling loss, to be honest. Some, I forget the name. There are some losses at the bend loss. That's called, because you have to bend the waveguide, there are some losses. Bend loss at each opening, and the overall loss as light propagates will increase. So what we did, we combined these 2 LETs together. The 2 LETs from 2 adjacent 6 transistor cells are combined together and illuminated with a single optical waveguide opening. This is the concept. Take the LETs from here, 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 combine them together, illuminate them with a single waveguide opening. By doing this, we can reduce the number of opening by a factor of 1, 2, 3, 4. That means if we used to have 2,000 openings, now we have only 500 openings. Got my point? Divide it by 4, slash it by 4, because we can use only 1 opening rather than using 1, 2, 3, 4 to eliminate the same thing. So what does it do? It reduces the bending loss by huge amount and also give compactness to the structure. Now, so this is a proposed 3D layout. Nothing much to discuss about it. These are some like long-term research, some calculations. I won't go into the details, but this is what it looks like. Let's go into the cartoon. How does it actually look? Because, okay, these things, if you are doing a PhD or master's, you'll understand. It will take time. It will take a couple of years. You'll understand. But we have to visualize things, right? That's what is important. We need to visualize that as researchers, as scientists. What's happening? These are the optical waveguides which we have. These are embedded inside the photonic layer. So I showed the waveguides just for you to understand, but in reality, they won't be seen. Even this top portion, believe me, it won't be seen. Now, if I would have embedded the whole thing inside this, you would have never seen anything, right? You will say, okay, that's a orange block. Nothing is visible. So just to make you see, I have showed the top of the waveguide. So these waveguides will actually be embedded inside the cladding. You know, core cladding in waveguides. I'll come into that. These waveguides are actually embedded inside the cladding. These green parts are the actual optical waveguides that are embedded inside the cladding. And this is the cross section. If we see from this portion, this way, the YX direction, XY direction. If we see from here, we will see the front portion of the waveguide, right? Now, design of optical waveguide system for the hybrid SRAM array. What material did we choose? Here we will design a silicon nitride on silicon dioxide waveguide. Why did we choose this? Okay, now the reason is silicon nitride. If you can see from this plot or from this, silicon nitride has a huge window of transmission for visible spectrum. It has a huge window of transmission in the visible spectrum, which means it transmits 300 nanometer of wavelength as well as it transmits 1 micron wavelength. That means all wavelengths starting from, say, let's say 300 nanometer. I'm just quoting a number. Uh, don't take my words on this. I forgot the numbers. It allows wavelength from as low as 300 nanometers to pass, as well as high as 1 micrometer to pass. That means it has a huge optical opening window, silicon nitride. So that's why you use silicon nitride. Also, you will see at wavelengths like blue light, which we have used. Blue light is around 400-ish or 380-ish nanometers. If you use blue light for optical transmission using a silicon nitride on silicon dioxide waveguide, silicon nitride is the core, silicon dioxide is the cladding, right? The total internal reflection happens due to the refractive index difference between the core and the cladding. So if you use that system, the optical insertion loss is very low for silicon nitride waveguide at 300 nanometer. Okay, like 300, not 300, 300 to 400, that window. It's basically ultraviolet to blue, not ultraviolet, violet, blue, those things. So in that window, which we are concerned about, we will be using that window only for our structure. The loss for that window, or exactly that portion of optical wavelength, like around 300 nanometer for silicon nitride and silicon dioxide, that combination, the optical loss is very low, almost zero. That's why you use silicon nitride. Now, this is the cartoon again showing the waveguide structure, which we have designed and optically simulated using a very sophisticated CAD tool. So this is the optical waveguide structure. These are the optical openings actually. Now, from where did I calculate these numbers? A lot of math, a lot of physics behind it. I don't want to get into the details of this, right? If you want details, you are like more than welcome to read my dissertation. These are not even in the paper, these are in the dissertation. So this is the optical waveguide structure. Now, here is the optical source where we will, or optical laser, whatever you call it, our laser, diode, we will push light into the optical waveguide and light will come out from this. We don't want light to come out from here. So to do that, we have to polish this structure with some reflecting, like say silver coating, so that light does not come out from here. It gets reflects and only comes out from these openings. And here we have the LETs vertically, lights coming out vertically and illuminating the LETs. Okay. Now these are some simulation results, nothing crazy, nothing too interesting. I'll show like, okay, now let me explain a bit. I won't go into the detail. So what I did was the tool which we were using does not allow us to measure optical power coming out from in a direction that's vertical to the direction of the actual source. So the source is pushing power in the horizontal direction in the XY plane, right? However, we need optical power to come out to the XZ plane. This is the Z plane, XZ plane. We need power to come out to the XZ plane. Now, the tool, for some reason, was not allowing us to measure power that's perpendicular to the direction of actual propagation. So what trick we do? First, we made the power come out. First, we did not have these optical openings, right? We just have the optical rectangular waveguide without the openings. And we measured how much power is transmitting, almost 98%. Done, good. Now we put these openings, 1, 2, 3. We have at least, I don't remember how many openings we have. Probably we have 500, I don't remember. Now we added these openings and we found as we have the openings, the power is decreasing as it comes, as it propagates. As it propagates here, because only the tool only allows power to be measured in the horizontal direction, not this. But we found a steady exponential decrease of the power as it propagates horizontally, which means where is the power going? Where is the power going? It's coming out through these guys, right? It's coming out from here. That means, yes, we can say the power is actually coming out in the vertical direction. Same, these are for different cross sections, 400 nanometer, 800 nanometer, 100 nanometer. Now, this is what we did. And we found if we use a 100 nanometer cross section, it's crazily bad. All of the power. So you can see almost more than 50% of the power is lost in transmission. Now, here comes, remember we told something in the third slide, mismatch, size mismatch. Here comes the thing. Now, you can definitely scale down. You can definitely scale down an electronic component to as low as 20 nanometer, 30 nanometer, right? Electronic component. Here you found as we scale down the optical waveguide cross section, this rectangular or square part, whatever you call it, to 100 nanometer. We just scale it down to, it's much more than electronic component. Even if you scale it down to 100 nanometer, which is again a large number, you see the optical power, it's almost lost, no transmission, 50% lost. This is the problem with photonics. This is the problem. We cannot scale down photonics because light is involved. Light is involved. We are using 300 nanometer wavelength light. That's visible spectrum because that's blue light. Below that, that's again the ultraviolet, which we cannot see. So if we want to stick to visible spectrum, we cannot go beyond 300 nanometer. That means we cannot miniaturize anything to less than 300 nanometer. 100 nanometer, it's crazily bad. You see the results. Now the final thing. I talked a lot of things. Did our optical SRAM actually work? How do we know that? So for that, we did a mixed mode TCAD simulation. We took our hybrid structure and we run a mixed mode simulation. Probably you know what is a mixed mode simulation. We did a electrical and optical, combine them in a single command file in TCAD and run for a single SRAM, for a single bit cell, to see if it's actually performing, if it's actually running. Because we have done something very crazy, right? We have replaced both the access FETs. We have thrown them out. And put something called LET. Also, we have replaced the electrical word line. We have trashed the electrical word line. We have put in an optical waveguide. So we have did so many things that are changed in a regular 6D structure. Now the big question, does the structure which we propose actually work? Let's see. Yes, it will work. Okay, there are some mathematical things. I won't go into the detail. Now, how do we know whether the SRAM is working or not? We did a butterfly curve plot. We plotted the IV of the whole SRAM, and we then reversed the IV for the one cross couple latch, did for the other cross couple latch, and plotted the butterfly diagram to see if the SRAM works. Yes, it absolutely works. This is for mixed mode simulation for a hybrid 60 cell. This is for the read. This is for the, this is for a regular 60 cell. This is for the hybrid cell. That means exactly this guy works. If it wouldn't have worked, what would have happened? This thing would have collapsed. Now we won't have this window opening. This square cannot be fitted inside. It will be something like a straight line, like this or this. Not a straight line, that curve, but not with such wide openings. Not with such wide openings. Not with an opening where we can fit a square. We cannot. If it wouldn't have worked, it will just collapse. Similar thing for a mixed mode simulation for a whole noise margin. Again, this is for a regular cell. I believe this is for a hybrid cell. That means it works. And for the right noise margin, that means it works. So our structure, yes, it successfully works. Now, variation of these are the butterfly curves. These are some optimization. It's fine. I don't need to go into the details. Now, I'll show something a bit interesting. Moving towards the optoelectronic logic for the next era of computing. Now, this is again a proposal. We did not have time at that moment to develop this, but this is a proposal. All of you know optical, not optical, CMOS, AND gates, CMOS, OR gates. How about an optically controlled LET-based AND gate? So what did we do? Again, dual simulation. When both the simulations are on, you will have an optical logic 1. When either of them are closed, you will have optical logic 0. How did we do it? I don't have the details. I have the details here, but I cannot explain. I have only probably 8 minutes. So actually the LET, which we discussed, can be made to operate in various regions. The subthreshold, the saturation depending on how much optical power or what optical wavelength we are using. Which means if we use blue light with a certain power, the LET will operate in a certain region of operation. However, for the same LET, if you use green light with a different power, different mode of operation. If you use red light with a different power, different mode of operation. So by tweaking and combining the powers, we can make it to work like optical logic. Similar thing for an optical OR gate. Same thing. Two illuminations, two different powers, two different wavelengths. Now, what's the advantage? The main advantage, which I can see, which is visual, which is visible. Forget about numbers, forget about how much energy efficient, forget about everything. How many logic gates, or not logic gates, sorry, my bad. How many field effect transistors are required to design a CMOS OR gate, two input OR gate? Anyone? How many how many field effect transistors or FETs are required to design a two input CMOS OR gate or a two input CMOS AND gate? Anyone? Any answer? It's pretty simple, right? How many? Any answer? Anyone? Come on, I want some interaction. Okay, that's fine. So for a CMOS OR gate or a CMOS AND gate, two inputs, we require 6 FETs, right? Because we first have to create a NAND or a NOR, because it's a CMOS complementary MOS. Then we have to put another inverter. That means 1, 2, 3, 4, 5, 6, right? We require 6 field effect transistor to design a single OR gate or a single AND gate. On contrary, we can do the same thing using a single LET. That means 6:1 ratio. We reduce the number by a factor of 6, right? That's a huge potential, right? Same thing for OR gate. That means if we could use this optical logic in place of electronic logic. Now, believe me, optical computing is the next era of computing in quantum computing. If you know quantum computing, it's basically photoelectronics or optics. In quantum computing, all the quantum computers that are made. So that this is the next generation of things that's probably gonna come in the next two decades, in the next 20 years. So there's a huge potential. Okay. Now some conclusion. Nothing fancy about it. Exactly same thing what I have been telling for the last 1.5 years, half hours. So low leakage, these things, this opens up a whole new avenue for electronic photonic integration, as you have seen. Now this principle which we have talked about today is fundamentally applicable to all photonic systems, not only like our LET structure. Whatever concepts we have, we can use it in other structures too, if you know how to do it. Also, those optical logic operations that I have showed you in the last slide, that also has a huge impact on quantum computing and those things, because these optical LETs, not only they can perform as optical logic gates, they have other functions too, which I cannot discuss here due to shortage of time, but you are most welcome to read this paper. I'll show you the paper. Give me a sec. It's in one of the papers, the details about the LET. This paper. If you are interested to know more about our structure, you can go to this paper. This paper. I'll send you the link if you need it. So you can go to this paper. You have all the details of the LET. So let me come back to the conclusion sides. Yes. So these are the few things. Like we have much more energy efficient computation. We have whole new avenues opening for us for quantum computing using optics or photonics. Now, the various obvious question which you should have asked me, I was expecting this question from the audience. What is the disadvantage of this structure? Now, if someone says you that a structure only has advantage with zero disadvantage, he or she is probably not correct. VLSI is all about trade-offs. So there are disadvantages of this structure, because any electronic or device, semiconductor device, cannot have only advantage. It's impossible. There are disadvantages. What's the problem with this structure? Anyone? Any idea? Any rough idea? It's the problem of miniaturization. Yes. Our structure is very energy efficient. It's highly, it has got extreme lightning speed. It cannot be miniaturized. It means you cannot have this structure inside your mobile phone. You cannot have these inside your smartwatch. You cannot. Because the optical part takes up lots of space. You saw it, right? If we scale down the optical waveline, optical waveguide to 100 nanometers, it does not transmit at all. It's bad. So we need to have a minimum of 400 nanometer cross 400 nanometer cross section for a single waveguide. So it takes up a lot of space. Now the question comes, then why did we even do this research? It is helpful in data centers. Now in data centers, you know, NVIDIA data centers, Google data center, Meta, Google, Meta, Apple, what else you can think about? All the big giants, Microsoft, they all have huge data centers, right? Where they store trillions of petabytes of data, huge data throughout for all the people in the world. Billions of people have all their things saved in social media, in Instagram, in Meta, in Facebook, in Gmail. Where do they actually store it? They store it in the data centers, right? So they have huge space for those supercomputers storing the data. Huge space means it's lasts for kilometers after kilometers, huge. So for those spaces, area is not the concern because you have a huge space, let's say size of say 1 kilometer cross 2 kilometers. That's a huge area. In those places, area is not the constraint, but energy consumption is. They consume gigawatts of power. That's huge. Now, in those places, if we could incorporate this energy efficient computing idea, which we discussed today, that will be a huge benefit. That will save billions of dollars, and it will save the world from energy crisis. There where our structure comes into play. It's not about miniaturization and compactness. Our structure never gonna fit inside your mobiles or smartwatches. Okay. Now, future prospects. These are the things which we could have done. We did not have time. So if we could develop a compact model for the LET and optical waveguide and do some SPICE simulation, that will be much faster, and it would have helped us to simulate a whole array, because currently we simulated only a 6 transistor cell, and for the mixed mode simulation of a 60 cell, it took around 72 hours for a single simulation, 72 hours. So you can imagine if it would have been array, it probably would have taken 1 month. So that's not possible. However, if we could develop some SPICE models, we could have run the simulation much faster. Some publications from my research work, a couple of research papers, a book chapter, and a US patent that's still pending. That's all from me. Thank you. Any questions?
Yeah, thank you, sir. Now this forum is open for queries and discussion. I request the participants to get involved in the discussion. Sir, I have one query as an previous participant. Yes, sir. So can you give insight to the effect of dark current in LEDs, and what is it, how to avoid this dark current effect?
Great question. Okay, to be very honest, I did not go in detail through the device simulation. So, okay, first of all, fundamentally, the LED is undoped. Now, if we have background doping, let's say generally we dope silicon with 10 raised to 15, 10 raised to 16 dopants. N-type, P-type doesn't matter. Let's say N-type. So if we do that, then the dark current will increase because let me go to the LED structure actually. Because if this nanowire is doped, even now, if the nanowire is doped, and even if we don't shine light, but apply a voltage at the two ends, there will be sufficient carriers here to conduct a current, which we don't want, right? We want only this structure to have current when we have light. No light, no current. That's the concept. Light. So if we dope the here, even without this light coming, we will have, and if we have this voltage, we will have current. So first thing, to minimize dark current, don't dope the nanowire. Undoped. Second thing, there is something called concept of asymmetric contacts at the two ends. So both of these contacts are ohmic contact. Okay, that means they have fundamentally the carriers can tunnel from this nanowire into the contact and vice versa, right? Because the potential well is very thin, right? If you see the quantum potential well, probably if a quantum well is formed, it will be very thin. Carriers can tunnel. However, if we could have an asymmetric contact, like asymmetric contact, by asymmetric contact I mean, let's say here we have a silicon nanowire, here we have a copper contact, here aluminum. I don't remember exactly what materials gives asymmetric contact, but the work function has to be different, right? So if we have asymmetric contacts, that can minimize the dark current, because at one side it will have ohmic, that's fine, the carrier can tunnel, but the other side, due to Schottky contact, the potential barrier would increase for the carriers. The carriers will see a high potential barrier. That means they cannot cross that. That means even if they're injected, they cannot cross that, and the overall circuit is, they cannot pass into the other side. That means the overall dark current will be much reduced. Okay.
Thank you, sir. Actually, I'm also interested in the optoelectronics instrumentation.
Okay.
And, yeah, that's why those information may be very much useful for my research work also.
Okay, that's great. Good to hear that.
Any other questions from participants, please? Okay, I think we don't have.
Hello, sir.
Okay, okay.
Yep.
Yes, please.
I have enjoyed a lot your work. So which type of simulation, which simulation we can use for this type of work?
You have to, yes, you have to use a center. You can use a Centros TCAD. Now for the optics part, you cannot use Centros TCAD. You can use Lumerical. There is one tool called ANSYS. Probably you have ANSYS Lumerical. You can use that for the optical simulation, and you can incorporate the results inside TCAD, Synopsys TCAD, to run a mixed mode simulation.
Okay, sir. So very interesting work it is.
Thank you.
Any other questions from our participants? Okay, I think we are done with the questions. So we are about to wrap up this session. As we have come to the end of this insightful session, ATAL online 60 faculty development program on energy sustainability climate theme, organized by Electrical Engineering Department, CIT Noshingod. I would like to take a moment to our distinguished speaker, Dr. Antardipan Pal, for sharing his experience with us. Your presentation was not only highly informative, but also extremely engaging. The depth of knowledge and clarity with which you covered topic like need of photonics, applications, LED structure, working, design and modeling has certainly broadened our understanding of photonics. On behalf of all the participant and organizing team, I would like to thank you for taking time to join us virtually and offering your expert perspective. We look forward to apply what we have learned and hope to have the opportunity to host you in future again.
Okay, that will be my pleasure. Thank you.
Yeah. We deeply appreciate your time, effort, and dedication. Thank you, sir.
Okay, thank you. Thanks a lot.
Yeah. Now, for our second session, please be with us, all the participants. Our second session will commence soon, and the next topic of our session is energy impact on cloud computing challenges and innovation. Okay.
Okay.
Thank you.
Thank you. Thanks, everyone.
Thank you, sir.
Okay. Bye. Have a good day. Bye.
Bye, sir.
Thank you, sir. Hello, everyone. Very good evening to all. Respected resource person, HUD of EE, all the faculty members and their participants. I, Sivaji Debarma, Department of Electrical Engineering, on behalf of Electrical Department, I welcome you all to the sessions of ATAL Online 6 Days Faculty Development Program on Energy, Sustainability and Climate Change. I am delighted to introduce our resource person, Sir Jay Tharwani, Software Engineer, USA, who has warmly accepted our invitation to join us today. He has completed his Bachelor of Engineering in the years 2014 from Mumbai University and completed Master of Science in Electrical Engineering in 2018 from University of North Carolina. Sir Jay Tharwani is an accomplished individual in the field of computer world like C, C++, Java, Python, HTML, CSS, etc. in software tool and in hardware tools like x86 based Intel and AMD server, Smart NIC, TI, MSP 430, VMC, etc. We are honored to have Sir Jay Tharwani here today to share his knowledge and experience with our participants. Today, Sir will talk about energy impact of cloud computing, challenges and innovations. On behalf of our electrical engineering department, I would like to welcome Sir Jay Tharwani and thank him for sparing his valuable time for us today. With that, I invite Sir Tharwani to start the session. Thank you again for joining us today. We are honored to have you with us. Sir,
Mhm. Yep. Thank you, everybody.
thank you, sir.
Yeah, hi. My name is Jay, and I'm here in Charlotte, North Carolina, in the U.S. Um, I so yeah, I mean it's pretty cold out here right now. It's negative temperatures over here. I hope in Tripura things are fine. Right. So, with not further ado, I'll just start the session. Thank you for hosting me today. And yeah, let's talk about some cloud computing and energy challenges. Okay, so I will share my screen right now. Okay, I need to. Shivaji, do you know how do you share screens in Google Meet? It's not giving me an option.
So just click on the present now button. It's just below.
I just seen camera, more options. Yeah, it's not giving me an option to share. I'm sorry.
Sir, one arrow is there. You can click on that.
Oh yeah, no, yeah, I had a smaller. Sorry about that. Okay. Now, can you see my screen? Okay, I think you can see my screen, right?
Yes,
Okay,
sir.
sir.
It is visible. Yes, sir.
It is
Oh.
visible.
It is visible.
Okay, so hi. So yeah, we'll be talking about the energy impact of cloud computing, right? So I'm Jay Tharwani. I've been part of NetApp Incorporated here in Raleigh, North Carolina. So it's a distributed storage operating system company which helps sell data storage solutions to big enterprises and the cloud like Amazon or the Azure or even Google Cloud. I have been part of Oracle Cloud, which was it's a new cloud provider, which is basically uh, competing with the big giants like Azure, Amazon Web Services, and Google Cloud. It's upcoming cloud. So I was one of their team members, helped building the cloud itself in one of their services. Right. Before that, and before that, I've also been part of an operating system software engineer at Intel in California. So yeah, that's me, right? And this is how I look like, right, in person. As I said, I am in NetApp, and I really like going to places. The top left is me at the salt plains in Utah. The bottom is left bottom is Colorado. The upper is I was in Sydney, and then again I was in Utah at a graduation ceremony. I really like to explore places and socialize with all living beings out there, including humans, baby humans, and animals. So that's mostly about me. So I will go forward and start the presentation. And disclaimer: this presentation is independent of my role at NetApp, right? I do not represent my organization in this presentation, right? And this content is purely based on my opinions and experiences, which I have had in the industry for some time. Yeah. So we have around 1.5 hours. So what I'll do is, probably take 1 hour to present. Please, if anybody has any questions in that time, please feel free to, interrupt me and ask questions, or else I'll try to save up around 15 minutes of my time for questions. Does that sound okay?
Sure, sir.
Yeah, I'll consider. Yeah, thank you. Okay, so cloud computing. I know many people, don't understand many times what cloud computing is. So I'll put this slide up to help understand. So what exactly is cloud, right? When you think about cloud, cloud is nothing but a business where these giants are trying to rent their own computers. That's exactly what it is, right? So whenever you push your data, and if it's going to the cloud, it's going to from some, Wi-Fi network to internet to the site hosted, and from a wire it'll go to a data center somewhere located in Seattle or anywhere in India or something, and get stored there in a physical computer, in a physical hard drive, or a flash cell, right, and all that stuff, right? So it's basically the business of renting computers, right? So what does cloud computing provide? So they provide us storage powers, processing powers, and you use these resources like storage, or how much computing power you want to use, by as much as you use, right? One of the main reasons why cloud has been very popular, and historically it was popularized by Amazon Web Services in 2006, because it gives organizations. So a little bit of history, right? So in 1992, the dot-com bubble burst. Right? No, sorry, in the 2000, the dot-com bubble burst. In 1992, the Linux was really popular as an operating system. And in 2000, when the dot-com bubble burst, what happened was, every company or every business, at least in the US, and which really trickled down to India as well, wanted an online presence, right? They wanted their business to be listed on the web. And for that, you need servers or data or computers which run those applications, which are serving you um, the information requested, like the how the business is and stuff like that, on demand. So you need computers which will be running their applications 24/7, right? So initially we were just having individual data centers for each kind of business, and stuff like that. So Amazon came with an idea, say like, hey, we will manage all your system resources to with us, and you just pay us money of how much ever you resources you use. And that was the birth of the cloud, right? And now they offer so much flexibility in terms of how much you want to use, how much storage you want to use, how much time you want to use, and the services they order. Like I was part of Oracle, and they had a collaboration with Cohere, which is an AI company, a startup, and which basically provides generative AI capabilities to your business. So basically, if your workload is being hosted in one of their clouds, the only thing you need to do to using AI is to make a function call, an API call, we call it. Basically, it's not a function call, but an API call in their network, and that's going to give you all the generative AI capabilities. So isn't that, it's very cool. It's like, you don't have to do any of the heavy lifting to use AI or generative AI, right? And so clouds offer a lot of storage flexibilities, compute flexibilities, and software flexibilities as well, and that is one of the reasons they are so much popular, right? Right. Any questions? I where I talked. Anybody has? I can go to the next slide. Okay. I'll consider that as a no. Right. Right. So now I mentioned a lot of things over here, right? The cloud and all that stuff, right? Like, let's see who are the big giants who are playing this game. Yeah. So the total market share of cloud computing, right, is $300 billion, right? And now, if you think, this is around 7% of India's GDP, right? It's a pretty huge number if you think about it. Secondly, it's around 27 lakh crores rupees, which is, people are paying to have their resources up to these companies, which we call the cloud. The biggest player in that is Amazon Web Services, right? And if you see the pie chart on your right, it is 33% of the total $300 billion. Then shortly up is Azure, which is Microsoft's Azure. And the third one is Google Cloud, right? So interestingly, all of these big companies are sitting in a small town in the state of Washington, here in the Pacific Northwest in the United States, and in a city called Seattle. Right, I was in Seattle for a month because I was working with Oracle, and yeah, interestingly, like every cloud business has thrived very well in Seattle. And I will not, I don't like that place because it rains a lot. It rains like 9 or 10 months an entire year, so it just becomes pretty depressing for me. I was like, no sunlight. But anyways, a little bit aside. So yeah, this is the market share. It's a pretty big number, and the other people, like, as I said, Oracle is, is one of the clouds which is like, really gaining momentum and increasing the business. Then we also have IBM and Alibaba Cloud. Alibaba Cloud mostly has the presence in China, right? It doesn't have much customers here in the US, right? So this is a very big number, and it's getting more popular because as generative AI is gaining more and more traction, these cloud providers are running their way basically to provide businesses the capabilities of generative AI as easily as possible, right? And Microsoft has also been pouring in their portfolio a lot of generative AI capabilities. If you see their PowerPoint, if you see their Excel, which I used recently, and all that stuff, they have a tag called Copilot where you can actually put in what you want to do in that Excel sheet, and it's going to do it for you. You want to put a pivot table, voila, it's there. You want to average it out, it's there. So the company is literally running right now to get these generative AI capabilities, and the cloud is a very interesting place where they can do it, because they're already giving so much compute power. Why not give this as well, right? So any questions on this slide? Okay, yeah, let me move to the next one. Okay, so now that we know the cloud, let's go with what are the energy challenges. Okay, right? I mean, you ask me, hey Jay, we have all this, big places, but what are the energy challenges? So the global energy data usage as I said, historically these were data centers which have now moved to the cloud, right? And so what these numbers I'll provide, which basically say the energy consumption, it's about with the data centers and the cloud together, because many data centers, individual businesses are planning to transition to the cloud as well, right? So the energy usage for all data centers is around 300 terawatt, right? And that's 1.3% of the global energy usage, which is quite a lot, right? And the hyperscalers, there's a term I'll use, hyperscalers, which I'll refer to these big giant cloud companies, which is AWS, Azure, GCP, and other providers, because they hyperscaler, they scale massive amount of compute capacity, at sites, so they will be hosting millions and millions of servers for other businesses to use, right? Now, this number is going pretty high, right? And the 2026 forecast is it can reach up to 450 terawatt hour. A little bit of background, how much terawatt it is. I think terawatt is 10 power 9 kilowatt hour, if I'm correct, or 10 power 12. Let me just clarify that. Yeah, it's 10 power 9 kilowatt hour. So it's quite a lot of energy, right? So yeah, that's where we are today. And this energy, anybody knows how much is the energy usage of India in 2022? Okay, so I'll give that number. So right, so India consumed like 15 terawatt hour, 1500 terawatt hour in the year 2022. So this 300 terawatt hour is around 5%, sorry, 1/5 of the energy which India is consuming. So yeah, so just to give an analogy, it's a pretty big number, right? And it is bound to grow. There's just, and remember that this number is only that we are using servers to be operational for businesses, right? That's it. So yeah, that's what we have in terms of energy. Any questions on this slide? Okay. Let me go forward. So I've put in this slide, because of the fact that it's a nice picture on what server data farm looks like. They have, you see that there are huge racks, and each rack has a slot. Each slot has like one server, and a server is a massive computer, right? It will have 400 cores, anywhere between 400 to 5,000 cores. It will have maybe terabytes of RAM, right? And it will have petabytes of storage, right? So many servers, and they have their own what do you say, buffer, or like how much storage and compute resources, but I'm just saying the highest number. So there are these millions and millions of servers stacked all around the globe in these kind of enclosements, and they call it as server farms, right? And this picture gives a nice analogy that they have grass at the bottom, and then they have these server shells, and they have many and many, and they are operating 24/7, right? And I have been to these server farms once, and they are so noisy. I tell you, people give you hearing aids to actually walk into these, because they're so noisy. And since they're so noisy, they also consume a lot of energy. They dissipate a lot of heat, and you need constant cooling facilities to also cool them, because or else there'll be thermal runaway problems where things burn out, right? So yeah, any data centers are major energy consumers, and there's a carbon emissions problem. They more rise of energy leads to burning of fossil fuels. Burning of fossil fuels leads to carbon emissions and environmental challenges, right? So that's where we are right now, and given the numbers. Any questions here? Okay. So let me move forward. Okay, so what are the key drivers of these rising power consumptions, right? Like, why do so ultimately in trade? I think one of the laws is, the more demand you have, that more supply will be made, because people want to make profit, and so so we are right now talking about the demand. What is the demand which is driving this huge adoption of cloud data centers, which is ultimately leading to more energy consumption, right? One of the things is, as you might all know, is the rapid compute intensive workloads in AI and ML training, right? So we have, after this thing of large language models, people are using so much GPU power for the training, and GPU are typically have much more cores packed and use a lot of energy, and these kind of servers with GPU capabilities are needed, and they're running training many times 24/7, right? That's increasing, that's increased compute resources, which increase a lot of energy demand. You have always have you have a data explosion, right? I don't know how many of you have last deleted your Google Photos, or you have deleted, your photos in your camera roll. You guys have a lot of storage capacity on your phones now, and most of that is being backed up in Google Photos or some other places so that you don't lose them. And right, many times they are duplicates, right? So there has been so this is only with one person. You have this millions and millions of people, not only in India but also all over the world using this, right? And you have a data explosion. You had, and in order to host data, you need data storage servers, and the storage servers need to be on so that the data is accessible, right? If it's on, it will consume a lot of energy, right? And there are always on services. Businesses want to be on all the time. Their websites need to be on all the time. That's a no-brainer. And you have services like AI services or any other services, all running all the time, because they want it as on demand. So that makes the server be on. That also consumes energy, right? There is a cloud and digital transformation all over the globe, right? And India is a very prime example for it. In the last, after COVID had hit, everybody of you would be knowing that, right? So there has been a digital transformation. Again, that requires servers to be on and consumes energy for running those servers and the cooling supplies. Now, there are the hyperscalers are pretty good in terms of power consumption and sustaining, but there are also a lot of places which say like, hey, we don't want our private data to be hosted on the public cloud, like government places and stuff. And they say that we will make our own data centers, and their servers are on even though nothing is running on them, and you have a very low server utilization, and so that also drives up the power, right? You have cooling requirements. In order to operate the server farm, not only you have servers who are consuming power, you also have cooling supplies which are also consuming power, right? And so it's a dual effect, right? So the most energy, I think one of the biggest thing is the least cooling equipment you have, or your hardware or the servers you're using, if they dissipate the least amount of heat, the less cooling supply will be needed, the less energy will be needed. That's one of the games of conserving energy in data centers is how do you maintain those cooling capacities, and optimized hardware, right? Then you have latency and edge computing growth, right? Like you have so many IoT devices. You have your small appliances. All of them these days connect to Wi-Fi, and it's so basically what happens is the compute is not being done on the device. It is only transferred to the network through the Wi-Fi to some server, and it's going to do the compute and do it, give back the response. This basically means is there need more compute capacity on the cloud, because all of these small devices which do not have compute capacities are connecting, and this is supposed to grow because all of these small devices, like internet was ubiquitous, now will also use AI in the future, right? And that will lead to more data transmissions to the server, getting, and server would need more compute capacity. You have, we always know, like, you know, a couple of years ago there was crypto all over, right? There was no everybody, used to see ads on Indian television also saying about crypto, right? And so crypto mining is very, very compute intensive. Mostly it is done by private data center owners, or even in the cloud, right? Because they need huge compute resources to do it, because they are finally trying to solve a lot of complex mathematical problems which use a lot of compute, right? So I think we are that bubble of, like, in crypto mining has reduced right now, but it's still there, and that also uses a lot of compute power, which uses a lot of energy. Then you have prevalence of legacy systems. I remember, IBM mainframe, if anybody knows about it, was released in 1950 to 1970, somewhere in between, and it is a very backdated system, right? But some of the companies in the financial sector still use it. They are still using the mainframes to store and run their application, which is like a very outdated system. People do it because they never got the capability, or they never came into the coherence that they wanted to transition into new systems. But these legacy systems are very, very not optimized, and they dissipate a lot of energy, right? Use a lot of energy, which dissipates a lot of heat and gives rise to energy challenges. Then you have inefficient hardware and software, right? You have older systems not optimized for energy efficiency, and you have older software running on them, right? So that's also one of the things. Then you have x86. So typically, historically, if you see, most of the server markets, or even in the cloud, servers which are being run are running on a microarchitecture called x86, right? Now, x86 was pioneered by Intel. I was fortunate to be a part of that company a couple of years ago, and so they, and one of the reasons they became so rich as a company, because they sold a lot of x86 architecture systems to a lot of companies which are still being used now. They fall into a category called CISC, which is complex inspection set computing, those kind of hardware. And but they dissipate a lot of heat. In contrast, we have another architecture set called RISC, which is reduced instruction set computing. You have heard about companies like ARM. They had they follow the RISC model. Most of your phones are running on a ARM instruction set, your iPhones, your Android phones, and stuff. Because also, one of the reasons they have chosen ARM for them is because they are inherently more energy efficient. But the server in the cloud and the data centers are still being used at x86, but prominently still there. So around ARM is basically 40% more energy efficient than a comparable x86 similar performance system. That's quite a lot, right? And and I already mentioned we have legacy hardware and software for business reasons, which are there. So these are the key drivers, why we are having more, firstly, adoption of the cloud, and more energy consumption of the cloud, and and many organizations around the world, they are going for how do we optimize this, because ultimately, if you are a cloud, if you are AWS, if you are Google, the less the more optimized your hardware is for energy efficiency, the less electricity bills you will have, the less operational costs you'll have, the less different equipments you'll need to manage heat dissipation, right? And which is good for the business, right? Ultimately, they are renting out computers, as I mentioned. So that will be that is in keen interest for these companies, and they do a lot of things, and we are already on the way to help with these energy challenges and with the leading data growth. Also, some other things which I'll continue in my next slides as we go through. Okay, any questions on this, please? Also, just a little bit of feedback. I hope I'm audible and I'm fine. Any concerns here? Am I audible?
Sir, you're audible.
Thank you. Okay, so let's discuss some of the challenges of the high energy. What happens, like, okay, we have high energy, so what, right? If someone asks me, so what, right? I mean, there are a lot of things, right? You have a lot of heat generation, bad for the climate. Have more heat. You have more electricity bills and operation costs. So more energy those equipments will use, the more cooling equipment you'll need to have to basically cool them. And then there's other different things they need to do in the data centers to actually maintain them. It's quite a long list. And then you have more capital expenditures, capex, right? Capital expenditures, which is money taken out from a company for power infrastructure. You're just paying money for just to maintain that particular data center for a cloud or any particular data center, right? You need increase cooling power. And then you also have to manage these high energy, you have very complex facility designs. So when I showed you the picture of a server farm, right? And if they are not designed in a proper manner, there can be a lot of thermal runaway problems, right? They need to be very designed very well, and so that they do not dissipate as much heat which is uncontrollable, right? And that's what there is, right? Then you have power grid limitations. Just imagine you have million servers at a facility which is around maybe 30-40 football fields, and how much energy can you source from there, right? Like that's a problem, right? Not every site will be capable to provide so much energy to just one particular area, right? And now you have carbon footprints. You are basically, when you are taking in energy from the grid or anywhere, one of the, even right now we have only 30% of our energy around the world is actually from renewable sources, which I say hydroelectricity or wind generations or stuff. Most of it comes from at the expense of fossil fuels, right? So you will burn fossil fuels so that you run that turbine which generates electricity for you. My dad was in a power plant, so I know a little bit how that works. And and then you need water. Now more inefficient your systems will be, the more heat they'll generate, the more water you will need for cooling. So you sometimes have water things also, right? Then you have different pressures from different stakeholders. You have the EU saying, coming up with all these laws that you can only have this much carbon emissions or this much things, or if you're using your facility and stuff like that. So there is also a pressure from different stakeholders, and there is also a risk of outages. Imagine you're running a whole new data center and something burns in the middle, right? Most thing is that not only that particular, the whole site might have to be turned off just because to contain the burning of that one particular server, not server, but an enclosed shell of servers. And you'll have to turn the site down. I mean, and that nobody wants it. Imagine which recently happened with the Microsoft CrowdStrike, where there was a global outage of airline companies, not able to schedule flights because their system was off, and their cloud was Microsoft Azure, which went down because of CrowdStrike. So, and then imagine that you are not able to get to a destination because somewhere the cloud is off, right? That is what happened in the US recently, and that's why cloud, the sector is so adamant on non-operational things, that it cannot stay offline. It just cannot. Okay. You have local energy regulations and green mandates, and then you have physical constraints on like how much big the server farm can be, how tall a particular server enclosure cell can be, and many other things. I don't come from the server infrastructure domain, but I do have some visibility like what can happen. So those are some physical constraints can be there, right? And then even now you have so massive amount of servers. How do you monitor them? How do you monitor that, okay, the thermal dissipation of one particular server rack is not exceeding this threshold, so that you can put in mechanisms so like, hey, this needs more attention, that's right. So you need those monitoring mechanisms to be in place as well. Monitoring and then controlling mechanisms to, okay, you know that it's being heated so much. How do you control to cool it off? Do you have those mechanisms in place? Do you have those things in place? So these are all things which are challenges for whenever you have high energy consumption, right? And some of them can be pretty nasty to deal with. Okay, any questions on this slide? Okay, let's go forward. Okay, so with time check, we have half an hour remaining. So I'll try to wrap it up. So now we know that, okay, what is increasing the cost, what is the challenges. Now we will go, what are the advances which the data centers and the cloud is doing for efficiency, right? I have more slides describing each of them, so I'll just give a brief. So you have, the design facility, the cooling, how there have been innovations in cooling, and you have the actual servers itself, like how do you make it more energy efficient, and then the software which runs on it, how do you make that such that it's not dissipating more power. And then they're also using AI for predicting that which server will go bad or which server will heat up, even before it had happened, so that they can take a preventive mechanism even before it has happened, right? Okay, so let's go with the first head, which is the data center facility and design, which have innovated. So many data centers I see, they for the cloud or even generally, they use pretty a cooler climate. So you will see a lot of places where there is natural cooling available. Maybe you can host a server in Alaska, right, where there is mostly winter times, or somewhere in Siberia or something like that, which is a cooler place. And so that helps you with the maintaining cooling equipment for, right. And the second one is the renewable site selection, which is basically you will have data centers which will be near a renewable energy power plant, and which will be serving energy directly from there, right. So so that particular data center is not contributing to fossil fuel emissions, because the energy is being sourced from a renewable power plant. Then there's something these cloud providers use. There's something, a metric, which is to count how much efficient a particular site is, by something called optimized power usage. It's a metric. It's called PUE, and it's the ratio of the amount of energy used by the facility, right, divided by the amount of energy used by the IT equipment, right. So as long as that ratio is near one, it's good, right. That means your energy used by IT equipment and your site is amount to be the same, right. Now you have data centers which basically have this ratio to be 2. So basically the amount of energy which is taken by the IT equipment is half of what it is being used in the entire site, which includes the IT equipment too. So when people used to operate their own data centers, sometimes it was close to 2, but these hyperscalers like AWS and Azure, they have reduced this metric to a 1.1. So there's only a 10% more use of energy to operate the facility versus the energy which your IT equipment is taking, right? So that's kind of the math behind it, which is pretty interesting if someone wants to delve into, like, how do you basically optimize your energy usage, right. And the other center facility design optimizations have been modular and prefabricated data centers. So the picture I showed you, over here. So uh, they are somewhere, fabricated in a factory and just shipped across, just like that, because they are optimized for airflow and and power distribution. That helps you to basically not have a lot of power dissipation, right? Even no, sorry, not power dissipation, but reduce the cooling impact, cooling facilities which might be used to in those data centers. Right, and you have optimized layouts which minimize your energy. Right, you have a lot of research has been done. How do you fabricate these even individual cells and the racks you store inside those cells so that minimizes energy waste. And then AI is also helping the data center. It is having smart cooling mechanisms, right? As I said, they are predictive analysis, like where something might need more cooling, and the AI automatically puts in more cooling to there. And then again, all of these advancements I'm saying are happening, right? But they're not there yet. We are still, a lot of data centers are kind of old fashioned, because once you are up running a facility and you have businesses running there, it's kind of hard to just transition it to a newer design, right? So but I hope that this would continue to happen throughout our future. Like, and mostly I've seen whenever there is an incentive of a business model, attached to this, it happens quicker. So I think that's the trajectory we are going on. Okay, now we also we discussed about design innovations. We also have cooling innovations, right? You have a free air cooling, right? You design at a facility which has more airflow, maybe somewhere at the top of a hill or something. It'll help you with free air cooling, right? And then there's a direct liquid cooling where you have direct liquid cooling mechanisms built into the data center, right? Which you have plates which are connected with water and stuff like that, which are controlled by AI. So that helps you to directly have cooling going on as needed. And there's immersive cooling, as like sometimes the equipment is immersed in a dielectric, and that the environment is giving you cooling itself. Right. I remember I heard a news article. This was when I was working at Intel, and that Microsoft had actually made a data center in a ship and immersed it into the ocean. And I am really not sure if that was a marketing gimmick or something, because you have a really networking problems over there. But they did that, and they ran that experiment for 2 years and 3 years, and the data center was operational, which was good for them. And so yeah, these are some things people are still working on, like how do we do that? Right? And then sometimes facilities also have heat reuse, right? So you have so much being, as I said, the data centers are noisy. They generate a lot of heat, and the heat you can reuse it for other places. Since the place is cold, if the data center is located, you can route that particular heat to heating places, right? So which industrial applications which use a lot of heat, or even household heating places, which I'm not really sure if they are doing that, but a lot of places need a lot of heat, so you can route that heat to somewhere else, right? So those are some cooling innovations. Okay, I think I didn't stop for questions on this and this slide. If anybody has any questions on either of these.
Participants, if you have any questions, you can ask. Sir, I have one question. Sir, how do data centers support emerging technologies like artificial intelligence, machine learning, or IoT?
How do they support, or like in from an energy perspective, or is in general, how do they support these particular technologies?
I mean, are they integrated with AI, machine learning, or IoT data centers?
Oh yeah, yeah. I mean, of course they are. So right, you have so much. So primarily AI, where is it being run on? If you ask a question, AI is very compute intensive. That means it needs a lot of resources. When I say resources, it needs a lot of computing cores, right? And you need a lot of memory, and it needs a lot of storage as well. So, and the computing traditionally, we had single core where we were like, your laptops where you have don't have GPU support, but you have these NVIDIA GPUs which are having 3 trillion cores, computing cores in just a single chip. And these are specialized hardware which these data center companies like AWS source. And finally, you have software models which these data center companies make, which are then basically deployed and given to customers for use. Like, hey, you can rent out a GPU from our facility and run your AI workloads on that. And that's what makes AI possible, right? IoT devices, similarly, Internet of Things is basically nothing but small, less compute intensive nodes connected to each other, and then using the Wi-Fi or any networking technology, just sending signals to. But the compute is happening there in the data center. That's how they support it. So you have specialized software in the data center which handles IoT, workloads and stuff, and then your device is just sending that and then getting. So as a customer and you're running any other company which deals with AI, IoT or anything, you can actually ask for those kind of instances or those kind of compute resources from these companies, and they will give it to you and charge you accordingly, right? So these are all supported. AI is supported by GPU, and IoT is just supported with a good networking bandwidth and specialized software in the data center. Does that answer your question?
Yes, sir. Thank you.
Yep. Okay. So,
So
yeah.
there is a basic question. So normally we are hearing this word cloud computing. Because here some providers are there to give this cloud computing. So why this word is used normally? What is the background for this cloud?
Cloud.
Why?
So, in one of the, miss, I'll tell you one thing is a lot of buzzword go in the tech industry, right? And one of the things is, I try my best to understand this and use this appropriately. But many people I see generally do not use it very appropriately, and sometimes even businesses as well, right? But answer to your question, cloud computing, basically what it is basically someone renting out their compute resources to you, right? And running all the applications will be run on that particular data center, and you're gonna just access it through the network. That's basically what cloud computing is. So again, right? So it might be a buzzword. I hope whoever is providing this knows what it is, right? And how. And most of the time they don't provide it. They provide with these big giants, which I mentioned right in this pie chart, which are AWS, Amazon Web Services, Microsoft Azure, Google Cloud, or Oracle Cloud, something like that, right? They will say this, but ultimately their things are running there because I don't think in India we have these big facilities of the cloud. Maybe I might be wrong. They may be there, but I'm not aware. Right? So does that answer your question, Miss?
Okay, thank you.
Okay. Okay. Any more questions? Okay, cool. So yeah, we mentioned about energy. We mentioned about data center facility design. We also discussed about what are the cooling innovations. Now the next innovation is, this is my favorite, is the high efficiency hardware, because I actually come from a domain. As I said, I used to work with Intel, and they were the pioneers of x86 architecture. And unfortunately, even though I'm working with them, I had worked with them, it is very intensive in terms of power, right? x86 architecture running from decades now, 30, 40 years or even more, for in servers at least, it consumes a lot of energy. And I mentioned that there is something called, they operate on something called CISC, which is complex instruction set computing. But you have Next, a different microarchitecture, which is a risk reduced instruction set computing, which is the ARM architecture, which was designed by ARM technologies, and and they dissipate 40% less power. So the industry, 80% of the servers are still on x86. They haven't been going on ARM, right? But these big hardware providers like Google, Amazon, and Microsoft have understood the relevance of ARM servers in in the data center. In fact, when I was actually at Intel, one of my executives went to spin off a new company which was dealing with ARM servers, because ARM were not a notable place there in the data centers. They may be on your phones, but not in the data centers. And so she has been pretty successful in that. And so they dissipate around 40% less power, and all of these big giants are making their own custom ARM-based servers, which is, if you hear the name AWS Graviton or Google Tau, a TP uses Tau platform units, I think, but Tau is their brand name for ARM-based servers, and it's good for them. The performance to cost ratio is also good. The only thing is they cannot be sometimes very highly compute intensive like x86 can be. Um, but yeah, but they're very good bang for your buck. They're releasing less energy, which is reducing the electricity cost for the cloud providers, and which is helping them. But what are the challenges they face? Most of the code which we see, okay, you have architecture, you bring in a good system, fine. What about the code? The code which you have written is still based out of for the x86 hardware, and people do not want to change that, right? There are many business critical applications still running x86 code. Rewriting them, doing that, they will take a lot of time, and because of that, the industry is very slow in adoption, or in the adoption of ARM based servers. But I think they would be the future, but it'll take a fair bit of time to reach there, because there is no uh, uh, you know there isn't very big incentive, but not enough such that we want to transition. No one wants to transition. If you do you want to transition, from your house going to someone else's other house or in a different city? Probably not. Even 10 folds more is changing your whole business pattern from one particular hardware software, to another. They're like, hey, I'm already making money, right? Why do I really want to change it right now? It's fine if I get a lower margin, but I don't want to change it, right? So that's kind of the mindset like most of the industry, has. Again, so we have these, which will be very power efficient. And then you also have high density racks and consolidation. So, which is basically you stack up servers more and more and more. So the cooling infrastructure which you will need in that data center will be pretty less, right? So that's what, right? So that was in hardware. Any questions here? Okay.
Participants, if you have any questions, please do ask.
Okay, I will move forward. And this is the crux of energy efficiency also. Why the hyperscalers are able to manage a high energy efficiency is because of virtualization. In fact, I had an opportunity to work on a virtualization software which used to power Microsoft's Azure's data center. And it's a very thin level of software which is called a hypervisor, right? So you have something called a hypervisor, which is manage the entire platform. So you have an entire platform which will having 400 cores, some terabytes of memory, and many terabytes of storage, right? Now, if it has 400 cores, but your application is basically just using 2 cores, and but the server is on, it's basically dissipating power, right? It's just sitting there just for one application, and which is a very not a very good uh, utilization of the whole system. So what they did was they came with this concept of a hypervisor which will run on the platform and which can run multiple operating systems on the same platform. Right. So if you have 400 C cores, they can run actually 200 different systems, but it is running on the same server. So basically 400 laptops worth of power on a single box, right? And which is virtualized using the hypervisor. And that really helps to, use the hardware fully. And since that is being used by multiple customers also, so you have American Airlines using it, you have Delta using it, you have some other using it. They're operating from the same box, so they give you a nice virtualized environment. They also give you with nice security policies to be employed, and many other things. They deal with a lot of challenges to even do this, but but they have to do it because it increases their what do you say, efficiencies, how much business they will do, and also reduce the power, which will again save on their infrastructure cost and stuff. So this is also one of the things which has always been there in data centers, and I think there is no cloud provider out there which does not use virtualization to effectively manage their data center infrastructure, right? And now you also have something called auto scaling and dynamic resource allocation, which basically is like someone wants 4 cores. The cloud provider gives them 4 cores. Um, Now their application now needs more compute resources, so they automatically scale it to 6 cores, more RAM, and it's dynamic. Supposedly, if you have a physical hardware, physical computer, you just cannot increase more and more RAM. You cannot yank out the motherboard, like the RAM in the motherboard, and then put some more in there, right? But the cloud provider is able to do it because of the facility of virtualization, right? So their dynamic resource allocation as and the business will just pay for what resources it's using. Supposing it needs more, they will pay for more. And again, you have AI for predictive maintenance. You have there is some workload which is not using the whole system. The AI will try to schedule it on a different server, which just needs that amount of resources, and shut that particular server on in sleep mode, and something like that. So these are very complicated technologies which they employ to optimize power, right? Which ultimately helps them as well, right? So yeah, so these were the 4 techniques, right, which are there: innovations in data center design, cooling innovations. You have high efficiency hardware, and you have optimizing, power with software and workload orchestration. You might hear the term Kubernetes as well in this, and that's a orchestration software which also does virtualization. It's part of the virtualization stack. Okay, and then now, okay, any questions on this? Okay, I will move forward. There are other techniques, right, like which are being used to conserve energy. Right? You have on-site solar and wind with cloud data center. You have monitoring and metering at a very granular level, how much heat a particular, even a node in a server is getting dissipated, right? And all this data with analytics goes to a dashboard, to a system administrator, which can actually look at it at real time, right? There's a lot of effort which has gone into making these kind of software systems for monitoring. Then you also have an open compute project, right? Open compute project is basically like we open source a lot of code these days. We are also open sourcing the design of the data center so that other people can also use it and contribute to it for a better energy efficient data center, right? This was started by Meta. Maybe it started in 2018. But that's what it is. It was an open compute project. So the information is available. You can use it, and you can also contribute it for if you think something can be designed in a better way. Right? Then you also have the Green Grid project, which is a consortium. Many companies are coming together. Like, how do you make it more greener? So the efforts are really underway, right? And the last decade has seen a lot of these efforts going. Only thing is how quickly can it lead to fruition is something we'll have to question and see, right? Because ultimately, again, leading less energy helps with better businesses for the cloud, which is very helpful. And they already foresee petabytes and petabytes of data being coming in from consumers all over the world, and that's going to be a challenge in terms of maintaining the equipment and also um, being a very profitable business, right? Um, I don't know if you guys know this. This is just an aside. I'm mostly done with my presentation, but the cloud also, Wall Street, which is the stock market here in the US, loves the cloud businesses. One of the reasons is they work on something called ARR, which is the annual recurring revenue. Right, so you are a subscription model, right? Just like Netflix, you subscribe and you have to pay every month. Similarly, the cloud is being the services of the cloud, services, software, platform, infrastructure need to be paid every month, as they use it. So there is a certain amount of revenue which is generated every year. So so people love it because, like, okay, every year you will have this fixed amount of revenue because you have these fixed customers which will be using your cloud. And if operated at very massive scale and very well, it's a pretty good business, but it comes with a lot of its own challenges, which a new cloud providers might have a hard time, because it requires a lot of capex, which is capital expenditures, to basically operate that business. And also clarifying with the other question which I got, which they told me. So many times when they mention cloud computing, it's mostly about a user able to understand what services a particular cloud provider provides, like AWS, Azure, or Google Cloud, and how do you operate those services. People even don't know how to operate those services. How do you use it, right? So many times, a lot of employers are also looking for, how do you use these services? Have you used the cloud? How you do it, right? But this is very separate from the discussions we are happening, which is more about energy over here. So yeah, that's what I'll say. Okay, any questions in this?
Participants, if there are any, please do ask. Sir, I think there are no more questions.
Okay, no problem. Okay, so there's a fair bit of things we discussed, right? Like, there are a lot of things, and I understand, if people do not come from the same background, might have a hard time to understand things. So, we discussed about energy challenges, what are the computing, and what are the innovations that are happening, and we are also embracing, renewable energy, and this diagram on the left, it is a very nice way. So basically, imagine that middle computer over there as a data center, right, which is sourcing power from the solar panels on the top right, and also from the top left, and it is sometimes also from the electric car and the windmills, and the industry is using that on the left, to using that cloud compute technology to use that energy. So it's a very interesting small picture, but yeah, it basically tells you what cloud computing is. Right? It's basically renting out computers at the end of the day, right? So this wraps up my whole presentation, and that's what I had to say. I will put in some my contact there in the chat. So in case people want to connect, ask questions or have any other things which they think I can be a help of, please feel free to reach out. And yeah, with that, I will, conclude asking like any other questions which I've put less data on the slide so that I can talk more, right? And so that rather than me putting in a lot of words over here, that's how I like to operate. But yeah, please feel free to ask questions if you have any.
So really, your information is really good. I have come to know about a new technology. So new informations we have gathered from your lecture. So thank you, sir.
Yeah, no problem. Thanks. It was a privilege to speak to you.
Participants, any further questions? Please do ask.
Yeah, hi Jay.
Hi.
This is Ardindu from Mumbai. I have a question for you.
Yes.
In your presentation summary, you mentioned that Seattle is having quite a few companies of cloud computing that their data center.
Right.
Yeah.
Sorry. I couldn't hear you properly with your question. Can you please repeat it if you
Yeah.
can?
This is regarding somewhere in your presentation at the beginning, you told there are quite a few companies like AWS and other big companies, cloud computing companies. They have their data center in Seattle.
Yeah, some of them have. They have data centers all around the world, but most of the controlling engineers, they sit in Seattle, right?
I
So
see.
yeah.
Not okay. So I thought that this, because this is, you told that it is heavily raining more than 200 days in a year, mostly in Seattle. So it will be humid atmosphere. So how the servers are surviving there? That was my question.
Yeah, no, it's a very interesting question. I thought the same when I went to Seattle, and I was like, I cannot survive here, so I came to North Carolina instead. But one of the things is it's a historic reason, right? Microsoft started in Seattle. Right?
Yeah.
This was back in very early 90s, right? Bill Gates has his home there, and then he established a base there. Now, as companies grew, AWS was the first to start a long, cloud business. It did it in 2006. Now, they wanted to hire engineers. How do you get from very good engineers who can help build the cloud? You source it from other companies. So they established a base there in Seattle, and they literally took out people from Microsoft to establish them. And this is how things grew. And then you had Google Cloud coming in. They're like, okay, we need more people who have cloud building experience. They also built it in Seattle. And even OCI, which I worked for personally, they tried in other places. They tried in California. They tried there. They couldn't gather enough, talent to spin off a proper cloud business. So they went back to Seattle. And there are other aspects. So this is one aspect. There's another aspect that Washington State. So Seattle is in Washington State, and it is a very tax favorable place, right? So it's tax free, right? And so companies they actually encourage people to establish businesses there in that state. So that is also one of the contributing factors. But the main contributing is the history of how the tech landscape has evolved because of Microsoft over there.
So in that it is economy, not the climate suitability.
Yes, it's more about like how much money people are getting, and they're like, okay, I'm fine with it.
Yeah, because Dropbox also have their
Yes.
Yeah.
And Dropbox.
My follow-up question is that what is the guarantee for this data piracy or data secrecy? How safe is data when you are going for AWS or Google or Microsoft?
How safe it is in terms of security, you're asking?
Suppose if my company want to purchase, cloud from AWS.
Right.
So what is the data safety or data secrecy? What is the guarantee that my data will not be siphoned somewhere else?
Yeah. No, it's a good question. So it's always these cloud companies, having worked there for some time also, one of the things I have realized, they make it an utmost importance to safeguard your data, right? They're like they are contacting with hardware vendors like Intel, Lenovo, Dell to see, can you have cryptographic, cryptography is a field where you encrypt your data, so on disk you encrypt the data, right? And so they are always interacting with these different players to have their cloud the safest way possible. So any cloud you go, AWS, Azure, or even Google Cloud, they have very good data security policies, right? And implementations as well. Now they also, in fact, they all there is an annual cloud AWS reInvent conference happens in Las Vegas every year, and they actually showcase like what security standards they're implementing, right? And then different industries, customers from different industries, like they see their conference like, hey, this makes sense. My data is even more secure. So they are marketing this strategy of their data security, and people, they like it and they take it. Most of their big customers are like big industries, right? Which are there. Um, so yeah, so that's how they so it's pretty secure, I'll say. That's what I'll say.
Okay, thank you very much. Your
Yeah.
session was quite interesting. I was having an impression that AWS is having almost 50% market share, but in your slide it's only 33%. Matlab very less in comparison to. It is, of course, in comparison to others, it is higher. But the way AWS is going ahead, I was saying they have already captured the 50% market share, but
Yeah.
practically not.
Yeah. So this is the
My
latest data from end of 2024, right? Previously, maybe in the early 2010s or something, maybe they might be having 50% at
yes,
that time. Yeah, but now Azure has picked up, right? Azure has picked up a lot of the share, and Google Cloud is also picking up, and OCI, Oracle Cloud, is also picking up a lot of the market share. So that's where they have lost some of them there.
okay. Thank you, John.
Okay. All right. Yeah. Any questions? Any more questions?
Participants, any questions? So I think there are no more questions.
Okay. Okay. Yeah. I think I'll wrap up saying, thank you. It was a real big privilege for me to speak at your college. And thank you. I'd like to personally also thank Ms. Dr. Mujumdar, who invited me here, and all the other organizers of the team who made it possible for me to speak over here. And yeah, that's what I'll say. Please, I will, after I stop sharing, I will drop in my LinkedIn profile over there, and also my email. If anyone has any questions, or you think I can be a good resource to reach out for something you are doing, please feel free to reach out, and I'll be happy to help. Okay. Thank you. I will stop sharing.
Sir, on behalf of Tripura Institute of Technology, I would like to extend our heartfelt gratitude to our ex-speaker, Mr. Tharwani, for this wonderful session he delivered. So your insightful presentation on energy impact cloud computing was truly engaging, informative, and thoughtful. Sir, we appreciate the time and effort you took to prepare and share your knowledge with us. Our sincere thanks for inspiring us, sir, motivating us, and sharing your expertise with us. Once again, sir, thank you so much for your fantastic session.
Yeah. Thank you, Anila. Thank you.
Thank you, sir.
Any also finally, I would like to ask, like, any feedback you like to give on my presentation, on something I would like I could have done better, something you liked, something you didn't like. It just helps me to be better. Anyone would like to share?
Yes, participants, anyone?
Okay, I think gives me a important thing, and I should put in a questionnaire at the end of the presentation. I think that have more part. But yeah,
Sure, sir.
yeah. Thank you. Thank you.
Okay, thank you so much, sir.
Yeah.
So participants, today we close this session. Tomorrow we'll meet at 6 p.m.